Imagine erasing everything you know. The screen you're watching, the chair you're sitting in, the air you're breathing, all gone. Now erase the Earth, the sun, every star in the sky, erase space itself. What's left? Nothing. Absolute nothingness. In a fraction of a second, emptiness transforms into a universe of infinite possibility. This isn't science fiction, it's the story of our cosmos. Join us on a journey through space and time as we delve into how everything began from nothing. In scientific terms, nothing refers to the absence of anything. That is, the complete lack of matter, energy, and even the absence of the structure of space and time. This concept can be quite perplexing, as our everyday experiences are filled with objects, forces, and interactions. In the realm of physics, however, it leads to deep philosophical and scientific inquiries about the nature of the universe itself. Interestingly, what scientists often refer to as nothing may not be entirely empty. Quantum physics, for example, reveals that even a perfect vacuum teems with fleeting particles that emerge and vanish due to the uncertainties inherent in energy states. This phenomenon is known as quantum fluctuations and challenges the very notion of a true void. It implies that so-called empty space is actually filled with potential and energy, inviting the idea that nothing can have its own complexity. Moreover, discussions about the origins of the universe often lead to speculation about nothing preceding the Big Bang. Some cosmologists theorize that our universe came into existence from a state of nothingness, where laws of physics as we know them did not yet apply. This idea raises profound questions about causality and existence, suggesting that the transition from nothing to the cosmos we see today may involve mechanisms we are only beginning to comprehend. Thus, nothing, in a scientific context, transforms from a simple absence into a subject of great intrigue and complexity. It invites contemplation about the very fabric of reality and poses significant questions for both physicists and philosophers alike, challenging our understanding of existence and the universe itself. Physicists describe the state of the universe before the Big Bang primarily as a singularity, a point in time where densities become infinitely large and the laws of physics as we know them cease to function properly. In this state, all matter, energy, space, and time were concentrated into an incredibly small volume, making it impossible to apply our current understanding of fundamental forces. This singularity existed prior to the expansion that initiated the universe as we perceive it today. In the framework of the Big Bang theory, some cosmologists suggest that the universe began as an extremely hot and dense point that underwent rapid expansion. However, preceding this expansion, there is a lack of concrete evidence, making the conditions of this primordial singularity a topic of extensive research and speculation. It raises intriguing questions about what came before the Big Bang, and whether time itself existed in any meaningful way during that period. Some theories propose that the universe emerged from a quantum state, or that it could have been involved in a cyclic process, with previous universes collapsing and then rebounding. Others consider the possibility that our universe is just one of many, suggesting that conditions might vary in other universes. Each of these ideas attempts to provide insight into what the cosmos was like before that monumental event. The study of the universe's state before the Big Bang continues to be a fascinating area of inquiry, driven by both theoretical exploration and observational evidence from the cosmos today. While definitive conclusions remain elusive, these theories push the boundaries of our understanding, inviting us to ponder the very origins of existence itself. The concept of true nothingness presents a significant philosophical and scientific challenge. In a strict scientific sense, nothingness is often viewed as a theoretical construct rather than a tangible reality. Various branches of physics, particularly quantum physics, suggest that even empty space is not devoid of activity. Instead, it is filled with quantum fluctuations that result in temporary particle creation. indicating that what we perceive as nothing is, in fact, a dynamic state teeming with virtual particles and energy. Philosophically, many argue that true nothingness cannot exist because it lacks properties, dimensions, or even a framework against which to define existence. This raises profound questions about whether we can even conceive of true emptiness. Some thinkers propose that the very act of asking whether nothingness can exist implies a contradiction, as it requires a context where nothing is a term we can understand or measure. From a cosmological perspective, the origins of the universe further complicate the notion of nothingness. Various theories suggest that our universe emerged from a state of conditions very different from what we observe today. Yet these states often involve fundamental physical laws or energy, elements that contradict the idea of sheer emptiness. Additionally, concepts like dark energy and the cosmological constant introduce further complexities, suggesting that hidden forces might be perpetually influencing the fabric of what we consider empty space. Ultimately, while the idea of nothingness captivates both scientists and philosophers, it increasingly appears to be an abstraction rather than a state that can be achieved. The exploration of this concept continues to deepen our understanding of reality and the universe, highlighting the intricacies and mysteries lying at the heart of existence. Our understanding of nothing has undergone significant evolution throughout history, influenced by philosophical thought, religious beliefs, and scientific inquiry. In ancient philosophy, particularly within Greek thought, nothing was often viewed in opposition to being. Philosophers like Parmenides famously argued that nothingness could not exist, since one could only speak of what is, marking a stark philosophical stance against the idea of void or absence. In medieval philosophy, discussions around nothingness were intertwined with theological concepts. The notion of creation ex nihilo, or creation from nothing, emerged as a central idea. This perspective posited that the universe was brought into existence by a divine entity from a state of nothingness. During this time, nothingness began to be viewed not merely as absence, but as a status that could be both philosophical and theological in its implications. With the advent of the scientific revolution in the 17th century, thinkers like René Descartes introduced a more empirical approach to concepts like existence and reality. The transition from philosophical to scientific discourse began to redefine the nature of nothingness. Newtonian physics allowed for the idea of a vacuum, prompting initial explorations into the emptiness of space. However, it was not until the development of quantum mechanics in the 20th century that our understanding of nothing transformed once again. Quantum physics revealed that even in empty space, energy and virtual particles exist in a dynamic state, challenging previously held notions of absolute nothingness. The realization that empty space is filled with potential raised fascinating questions about the fundamental nature of the universe. Today, the exploration of nothingness encompasses complex theories in both cosmology and philosophy, indicating that our understanding remains a blend of deep inquiry into both the physical and metaphysical realms. Quantum fluctuations in a vacuum refer to the temporary and spontaneous appearance and disappearance of particle-antiparticle pairs that arise from the uncertainty inherent in quantum mechanics. According to the principles of quantum theory, even in what we perceive as empty space, there is a constant energy field that allows for these brief occurrences. These fluctuations challenge our traditional understanding of a vacuum as a complete void, suggesting instead that it is a dynamic and active environment. These quantum fluctuations demonstrate that a vacuum is not truly nothing. Instead, it acts as a stage where virtual particles can manifest for incredibly short periods, influenced by the uncertainty principle. This principle essentially states that certain pairs of physical properties, such as position and momentum, cannot both be precisely determined at the same time, allowing for these transient fluctuations to occur. Consequently, even in empty space, there exists a foundation of energy and possibility, meaning that true nothingness, devoid of all properties and effects, is effectively unattainable within our current understanding of physics. Furthermore, quantum fluctuations have significant implications in cosmology and the understanding of the universe's beginnings. The energy fluctuations present in the vacuum are believed to have played a crucial role just after the Big Bang, contributing to cosmic inflation, the rapid expansion of the universe. These fluctuations could lead to variations in density, ultimately giving rise to the large-scale structures we observe in the cosmos today. Thus, while we may think of a vacuum as a state of nothingness, quantum fluctuations reveal a more intricate reality. They showcase that even in the absence of matter, the universe is far from empty. It thrives with potential and energy, complicating our exploration of what it truly means to encounter nothing. The Big Bang Theory, which posits that the universe began from an extremely hot and dense state approximately 13.8 billion years ago, is supported by several key pieces of evidence. One of the most pivotal is the observation of cosmic microwave background radiation, which serves as a remnant of the heat from the early universe. This faint glow permeates all of space and was discovered in 1965 by Arno Penzias and Robert Wilson. Its uniformity and specific temperature of around 2.7 degrees above absolute zero provides strong support for the rapid expansion and cooling that occurred shortly after the Big Bang. Another significant piece of evidence comes from the redshift of distant galaxies. As Edwin Hubble demonstrated in the early 20th century, light from galaxies is shifted towards the red end of the spectrum, a phenomenon indicative of those galaxies moving away from us. This observation implies that the universe is expanding. The relationship between distance and redshift suggests that, if we were to extrapolate back in time, all galaxies originated from a singular point, reinforcing the idea of a cosmic beginning. Additionally, the abundance of light elements in the universe aligns closely with predictions made by Big Bang nucleosynthesis. According to this model, during the first few minutes after the Big Bang, protons and neutrons combined to form helium, deuterium, and small amounts of lithium and beryllium. Observations of these light elements in the universe mirror the expected ratios produced in the model, providing further validation of the theory. Finally, large-scale structures in the universe, such as the distribution of galaxies and galaxy clusters, also support the Big Bang theory. The patterns observed can be traced back to the initial conditions set by the Big Bang and the subsequent inflationary period. Observations made through telescopes and cosmological surveys help map this structure, reinforcing the narrative of an evolving universe beginning from a highly concentrated state. Collectively, these lines of evidence form a robust framework supporting the Big Bang theory and our understanding of cosmic history. Edwin Hubble's groundbreaking discoveries in the early 20th century provided a critical foundation for the development of the Big Bang theory. One of his most significant contributions was the observation that distant galaxies appear to be moving away from us, a phenomenon known as redshift. This redshift indicates that the light from these galaxies is stretched to longer wavelengths due to their motion, suggesting that the universe is expanding. Hubble's work demonstrated a correlation between the distance to galaxies and their redshift, a relationship now understood as Hubble's law. This correlation had profound implications for cosmology. Before Hubble's discoveries, many astronomers viewed the universe as static and unchanging, dominated by the belief in an eternal cosmos. However, the notion that galaxies are receding from one another implied that, at some point in the past, they must have been much closer together, supporting the idea of a beginning for the universe. This expanding universe model laid the groundwork for the Big Bang theory, which posits that the cosmos originated from an incredibly hot and dense state approximately 13.8 billion years ago. In addition to his observational evidence, Hubble's findings helped shift the scientific community's focus from a static universe model to one that embraced dynamic change and evolution. His work paved the way for physicists and cosmologists to further explore the implications of an expanding universe, including the development of theories regarding cosmic inflation, structure formation, and the dynamics of dark matter and dark energy. Hubble's discoveries also illuminated the need for a comprehensive theoretical framework to explain not only the observed expansion, but also the origins and evolution of the universe. As a result, his contributions played a key role in the eventual acceptance of the Big Bang theory as the prevailing cosmological model, profoundly influencing our understanding of the universe's history and its continuing evolution. The initial state of the universe right after the Big Bang was one of extreme conditions, characterized by incredibly high temperatures and densities. In those first moments, the universe was a hot, dense plasma made up of fundamental particles such as quarks, electrons, and neutrinos. The temperatures were so elevated that conventional atomic structures could not form. Instead, particles existed in a state of chaos and energy, annihilating and recombining at an astonishing rate. As the universe began to expand, it started to cool rapidly. The cooling allowed quarks to combine and form protons and neutrons within the first few microseconds. This rapid transformation laid the groundwork for the formation of atomic nuclei through a process known as nucleosynthesis. Within just a few minutes, the universe produced significant quantities of helium, deuterium, and small amounts of lithium and beryllium, contributing to the elemental composition we observe today. Following this nucleosynthesis phase, the universe continued to expand and cool. About 380,000 years after the Big Bang, temperatures dropped sufficiently to allow electrons to combine with protons, forming neutral hydrogen atoms. This process is known as recombination and led to the decoupling of matter and radiation. As a result, photons could travel freely through the universe, marking the release of cosmic microwave background radiation, which we can still detect today. Thus, immediately after the Big Bang, the universe was an incredibly hot and dense environment filled with energetic particles. It underwent rapid expansion and cooling, leading to the formation of the first atomic nuclei and later neutral atoms. This set the stage for the subsequent formation of stars, galaxies, and the complex structures we observe in the universe today. Estimating the age of the universe is a complex process that combines theoretical modeling with astronomical observations. The current best estimate places the age of the universe at approximately 13.8 billion years, determined through several interrelated methods. One of the primary techniques used to estimate the age of the universe involves analyzing the expansion rate measured by Hubble's law. By observing distant galaxies and determining their redshifts, astronomers can establish how fast the universe is expanding. This expansion rate, known as the Hubble constant, offers a direct method to extrapolate backward in time to the moment of the Big Bang. The result provides a timeline for the universe's expansion, allowing scientists to gauge its age. Another crucial method comes from studying the cosmic microwave background radiation, the remnant heat from the Big Bang. Measurements made by satellites such as the Planck spacecraft have meticulously analyzed this radiation to provide insights into the early universe's conditions. By examining the fluctuations in temperature and density in this background radiation, researchers can infer how the universe has evolved over time. These measurements contribute significantly to our understanding of cosmological parameters, which in turn helps refine the age estimate. Additionally, astronomers estimate the ages of the oldest known stars and star clusters within our galaxy. For example, globular clusters, which contain some of the oldest stars, provide a minimum age for the universe since these stars must have formed after the Big Bang. By studying the stellar populations and employing models of stellar evolution, scientists can determine how long these stars have existed. By combining these various methods, analysis of cosmic expansion, observations of cosmic microwave background radiation, and measurements of ancient stars, scientists arrive at a coherent estimate for the age of the universe. This multifaceted approach ensures that the estimate is robust and accounts for a range of cosmic phenomena and principles, thus grounding our understanding of the cosmos in a solid scientific framework. Cosmic microwave background radiation, often referred to as CMB radiation, is the remnant glow of heat left over from the Big Bang, filling the universe with a faint uniform radiation. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB is a critical piece of evidence for the Big Bang theory. It is a form of electromagnetic radiation that has a temperature of approximately 2.7 degrees Kelvin, meaning it is just a few degrees above absolute zero. The significance of the CMB lies in what it represents: a snapshot of the universe when it was about 380,000 years old, long after the initial explosive event. At this age, the universe had cooled enough for electrons and protons to combine and form neutral hydrogen atoms. This process of recombination allowed photons to decouple from matter, enabling light to travel freely through space. The CMB is essentially the afterglow of that moment, providing astronomers with a glimpse into the infant universe's conditions and composition. CMB radiation carries with it rich information regarding the density fluctuations that existed shortly after the Big Bang. Analyzing the slight variations in temperature and density across the CMB allows scientists to infer the distribution of matter in the early universe. These fluctuations ultimately seeded the formation of galaxies and large-scale structures we observe today. The observational data collected from missions such as the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft have vastly improved our understanding of the universe's composition, including the proportions of dark matter, dark energy, and normal matter. The CMB also serves as a powerful tool for testing cosmological models. By comparing theoretical predictions of the CMB's properties with actual observations, scientists can refine their understanding of the universe's evolution, leading to insights into fundamental questions about its origins, structure, and fate. The cosmic microwave background radiation is not only a remnant of the Big Bang, but also a crucial window into the history and dynamics of the universe itself. Inflation theory proposes that the universe underwent an extremely rapid expansion during the very first moments after the Big Bang, specifically from approximately 10 to the power of minus 36 seconds to about 10 to the power of minus 32 seconds after the event. This rapid expansion factor effectively stretched the universe from subatomic scales to sizes much larger than our current observable cosmos in a fraction of a second. Inflation explains several key observations about the universe that classical Big Bang models struggle to address. One of the main contributions of inflationary theory is that it accounts for the uniformity of the cosmic microwave background radiation. During the rapid expansion, regions of space that are now observed as separate and distant became causally connected, leading to a uniform temperature across the early universe. This uniformity is critical because it helps explain why the CMB exhibits only slight fluctuations in temperature, which are crucial for understanding the subsequent structure formation of the cosmos. Inflation also explains the observed flatness of the universe. As the universe expanded exponentially, it smoothed out any initial curvature, resulting in a geometry that is very nearly flat. Inflation allows for a homogeneous and isotropic universe, resolving the so-called flatness problem that questions why the observable universe appears to have such a precise balance between being open and closed. Another significant aspect of inflation is its role in producing the quantum fluctuations that eventually seeded the large-scale structures we observe today, such as galaxies and galaxy clusters. During this rapid expansion, tiny quantum fluctuations in energy density were stretched, leading to regions of varying density. As the universe continued to expand and cool, these fluctuations became the seeds for gravitational collapse, giving rise to the cosmic web structure. By providing this framework for understanding the early universe's rapid expansion and its implications, inflation theory has become an integral part of modern cosmology. It not only offers explanations for various observed phenomena, but also integrates seamlessly with the Big Bang model, together enriching our comprehension of the universe's origins and development. Despite its success in explaining many aspects of the universe's origins and evolution, our current understanding of the Big Bang theory comes with several limitations that highlight the ongoing challenges faced in cosmology. One primary limitation is the inability to fully describe the conditions that existed at or before the singularity itself. The laws of physics, particularly general relativity and quantum mechanics, break down under the extreme conditions of density and temperature present at the very beginning of the universe. As a result, scientists have yet to formulate a comprehensive theory of quantum gravity that can seamlessly unite these two frameworks. Another significant challenge is the nature of dark matter and dark energy, which together constitute approximately 95% of the universe's total energy content. While their existence is inferred from their gravitational effects and the accelerated expansion of the universe, their precise nature remains elusive. The Big Bang theory does not inherently address what dark matter and dark energy are or how they interact with ordinary matter, which limits our understanding of several fundamental cosmic processes and the overall dynamics of the universe. Moreover, there are unresolved questions regarding the uniformity and anisotropies observed in the cosmic microwave background radiation. While inflation theory offers a compelling explanation for the initial uniformity, variations in temperature still present theoretical difficulties that require further investigation. Questions remain about the mechanisms that led to the specific scale of fluctuations observed and how they translate into the large-scale structure of the universe. Finally, the potential for other cosmological models that challenge or provide alternatives to the Big Bang theory also poses limitations on our understanding. While the Big Bang theory remains the leading explanation for cosmic origins, the existence of alternative models, such as cyclic models or those involving multiverses, invites ongoing scrutiny and the need for experimental evidence. As our observational capabilities improve and our theoretical frameworks evolve, new insights may continue to reshape and refine our understanding of the universe and its inception. Fundamental particles are the building blocks of matter and are classified into two primary categories, fermions and bosons, with fermions being the particles that make up matter. Within the realm of fermions, the most important particles are quarks and leptons. Quarks are fundamental constituents of protons and neutrons, which in turn make up atomic nuclei. There are 6 different flavors of quarks, known as up, down, charm, strange, top, and bottom. Protons are composed of 2 up quarks and 1 down quark, while neutrons consist of 2 down quarks and 1 up quark. Quarks are never found in isolation. They are always bound together, held by the strong nuclear force, mediated by particles called gluons. Gluons are the force carriers of the strong force and act as the glue that holds quarks together inside protons and neutrons. Leptons are the other primary category of fundamental particles that make up matter. The most well-known lepton is the electron, which orbits the nucleus of an atom. Electrons carry a negative electric charge and are essential for forming chemical bonds between atoms. In addition to electrons, there are 5 other types of leptons: the muon and tau particles, along with their corresponding neutrinos, muon neutrinos and tau neutrinos. Neutrinos are extremely lightweight particles that interact very weakly with matter, making them difficult to detect. They are produced in various processes, including nuclear fusion in stars and during certain types of particle decay. Together, quarks and leptons account for all of the ordinary matter found in the universe. While these fundamental particles are governed by fundamental forces such as electromagnetism, the weak nuclear force, and the strong nuclear force, the gravitational force is considered separately, acting on the mass of these particles. Understanding these fundamental particles helps scientists explore the nature of matter, the forces acting upon it, and the underlying structure of our universe. In the early universe, immediately following the Big Bang, conditions were so extreme that particles were in a state of high energy and density. During the first moments after the Big Bang, the universe was filled with a hot, dense plasma composed of fundamental particles, including quarks and leptons. The formation of quarks and leptons occurred during a sequence of events driven by cooling and the expansion of this primordial plasma. As the universe expanded, it began to cool rapidly. Within the first microseconds, the energy levels in the universe allowed quarks to emerge as a result of high-energy interactions among more fundamental entities. According to quantum chromodynamics, the theory that describes the strong interaction, quarks are always produced in pairs or triplets. According to quantum chromodynamics, the theory that describes the strong interaction, quarks are always produced in pairs or triplets. Thus, as the universe cooled, quarks combined to form protons and neutrons through specific interactions governed by the strong nuclear force. The formation of leptons, like electrons, also occurred in this hot, dense environment. During the cooling period, the energy available allowed for the production of various leptons through processes such as pair creation, where energy converts into particle-antiparticle pairs. For instance, when photons, particles of light, had enough energy, they could generate electron-positron pairs. Positrons are the antiparticles of electrons, and together they showcase the symmetry inherent in particle physics. As the universe continued to expand and cool over the first few hundred seconds, a key process known as Big Bang nucleosynthesis took place. This involved the formation of atomic nuclei from protons and neutrons, leading to the creation of the lightest elements, such as helium, deuterium, and lithium. During this time, the density and temperature eventually dropped enough to allow for the stable formation of matter. Overall, quarks and leptons formed under conditions of extreme energy and rapidly changing temperatures following the Big Bang, driven by fundamental forces and interactions. The culmination of these processes set the stage for the formation of the matter that constitutes the universe we observe today. The Higgs boson is an elementary particle that is associated with the Higgs field, an invisible energy field that permeates the universe. The existence of this particle is crucial because it provides an explanation for why other fundamental particles, such as protons and electrons, have mass. Through a process called spontaneous symmetry breaking, particles interact with the Higgs field and gain mass as they move through it, akin to a person wading through thick mud. This interaction is what allows particles to slow down and acquire the mass necessary to form the matter we see around us. Discovered in 2012 at the Large Hadron Collider, the Higgs boson confirmed a vital aspect of the standard model of particle physics. This model describes the fundamental particles and forces that govern the universe. Prior to its discovery, scientists had theorized about the Higgs boson for decades, yet its detection was a monumental achievement that proved to be a key missing piece of the puzzle regarding particle physics. The significance of the Higgs boson extends beyond just confirming the standard model. By understanding the properties of this particle, researchers hope to unlock further mysteries about the universe. For instance, insights into the Higgs field could help explain phenomena like dark matter and why the universe is dominated by matter instead of antimatter. Such knowledge could revolutionize our comprehension of the cosmos. Moreover, the discovery of the Higgs boson showcases humanity's triumph in scientific inquiry, illustrating our ability to explore the tiniest building blocks of nature. It emphasizes the collaborative efforts of scientists from around the world and highlights how fundamental research can lead to greater technological advancements, inspiring future generations to delve deeper into the mysteries of the universe. Particle accelerators are extraordinary machines that propel charged particles, such as protons and electrons, to nearly the speed of light before smashing them into one another or into stationary targets. This process of high-energy collisions generates conditions similar to those just after the Big Bang, allowing scientists to observe the fundamental processes of particle formation. By studying the debris from these collisions, researchers can identify new particles and explore their properties. When particles collide at such high speeds, they can transform into a variety of other particles, a phenomenon described by Einstein's famous equation relating energy and mass. This ability to convert energy into mass is essential for discovering elusive particles like the Higgs boson. Detectors surrounding the collision points capture the resulting particles, and advanced technology analyzes the data to reconstruct the events that occurred during the collision. Through this meticulous examination, scientists can measure the parameters of newly formed particles, such as their mass, charge, and decay patterns. These observations can confirm or refute theoretical predictions about particle behavior, thus refining our understanding of the fundamental forces and components that make up the universe. The results can either validate existing theories or provide new insights that lead to innovative hypotheses in particle physics. Particle accelerators, such as the Large Hadron Collider, are not just about discovery. They also foster international collaboration, bringing together physicists from diverse backgrounds to tackle some of the most profound questions in science. The technology developed for these accelerators often finds applications beyond particle physics, influencing fields like medical imaging and materials science, showcasing the far-reaching impact of this approach to studying the universe. Antimatter consists of particles that are counterparts to the particles of ordinary matter, having the same mass but opposite charge and certain other properties. For instance, the antimatter equivalent of an electron is called a positron, which carries a positive charge instead of a negative one. When a particle of matter encounters its antimatter counterpart, the two annihilate each other, releasing energy in the form of gamma rays. Although antimatter exists in small quantities and can be produced in laboratories, the observable universe is predominantly composed of matter. The question of why there is an apparent asymmetry between matter and antimatter is one of the most intriguing puzzles in cosmology and particle physics. In the early moments after the Big Bang, it is believed that equal amounts of matter and antimatter were created. However, as the universe expanded and cooled, a slight imbalance occurred, leading to a surplus of matter over antimatter. This imbalance is puzzling because the laws of physics as we understand them do not favor the creation of one over the other. Several theories propose explanations for this matter-antimatter asymmetry. One suggestion is that certain decay processes involving subatomic particles may violate a principle called charge parity symmetry. This violation could lead to conditions that favor the production of matter over antimatter. Additionally, some researchers explore the idea of unknown interactions at high energies that may discriminate between matter and antimatter, suggesting new physics beyond the current understanding encapsulated in the Standard Model. Understanding why our universe is predominantly matter can provide profound insights into the fundamental laws of nature. Solving this mystery may reveal new particles, forces, or principles that science has yet to uncover, offering a deeper comprehension of not only the universe's origins, but also its ultimate fate. Exploring the nature of antimatter and its relationship to matter could reshape our perspective on the cosmos and our place within it. The first atoms formed during a period known as recombination, which occurred approximately 380,000 years after the Big Bang. Initially, the universe was a hot, dense plasma where protons, neutrons, and electrons existed in a chaotic state. In this extremely high-temperature environment, particles were constantly colliding with enough energy to prevent the formation of stable atoms. As the universe expanded, it began to cool, allowing these particles to lose energy and eventually combine to form the first neutral hydrogen atoms. At this pivotal moment, as the universe cooled to about 3,000 degrees Celsius, protons and electrons combined in a process known as recombination. The negatively charged electrons were captured by positively charged protons, leading to a significant drop in the density of free electrons. This transition allowed photons, light particles, to travel freely through space for the first time, resulting in what we now recognize as the cosmic microwave background radiation. This faint glow is a remnant from that early era, providing evidence of the universe's hot and dense beginnings. The formation of hydrogen atoms was critical, as they made up the majority of the matter in the universe. However, helium was also produced during the first few minutes of the universe's existence through a process called Big Bang nucleosynthesis. This process allowed protons and neutrons to combine and form helium nuclei, resulting in a universe composed mainly of hydrogen and helium. These elements serve as the building blocks of stars and galaxies, ultimately leading to the complex structures we observe today. As stars formed from clouds of gas composed primarily of these first atoms, nuclear fusion processes within them produced heavier elements. This iterative process of stellar evolution and supernova explosions laid down the foundation for the rich variety of elements necessary for the formation of planets and life itself. The journey from the first atoms to the elements that make up everything around us is a testament to the dynamic evolution of the universe. Primordial nucleosynthesis refers to the formation of light elements during the first few minutes following the Big Bang, specifically in the time frame of about 3 to 20 minutes after the universe began. During this brief period, conditions in the universe were extremely hot and dense, allowing for nuclear reactions to occur among protons, neutrons, and other particles. The primary elements produced during this process were hydrogen, helium, and trace amounts of lithium and beryllium. As the universe expanded and cooled, protons and neutrons began to combine through nuclear fusion reactions. Initially, the universe consisted mostly of free protons and neutrons. As temperatures dropped to a range suitable for nuclear interactions, these particles started to fuse. The most significant reaction was the formation of helium from hydrogen. This involved the fusion of two protons to create a deuterium nucleus, which is a hydrogen isotope consisting of one proton and one neutron. Further reactions then allowed deuterium nuclei to combine with more protons and neutrons to form helium nuclei. By the end of primordial nucleosynthesis, it is estimated that about 75% of the normal matter in the universe was converted into hydrogen, approximately 25% into helium, and a trace amount into lithium and beryllium. These light elements formed the fundamental building blocks for stars and galaxies that appeared later in the universe's history. The relative abundances of these elements, predicted by the theory of primordial nucleosynthesis, match remarkably well with observations we make today, confirming the accuracy of our understanding of the early universe. The significance of primordial nucleosynthesis cannot be overstated. It not only provides insight into the conditions of the early universe, but also lays the groundwork for the formation of more complex elements through stellar processes millions of years later. The understanding of these processes helps scientists unravel the history of the cosmos and the origins of the matter that makes up everything we see around us. Hydrogen and helium became the predominant elements formed after the Big Bang due to a combination of factors related to the nature of nucleosynthesis and the conditions present in the early universe. Initially, the universe was a hot, dense environment filled with elementary particles, primarily protons, neutrons, and electrons. As it expanded and cooled, conditions became favorable for the formation of atomic nuclei. During primordial nucleosynthesis, which took place within the first few minutes after the Big Bang, the temperature and density were just right for protons and neutrons to undergo nuclear fusion. Protons, which are the nuclei of hydrogen, were the most abundant particles in this phase. Neutrons, though less abundant, also played a critical role. They combined with protons to form deuterium, an isotope of hydrogen. The stability and simplicity of the hydrogen nucleus, comprising just one proton, allowed it to dominate in abundance. As conditions continued to evolve, deuterium nuclei could further fuse to create helium nuclei, which consist of two protons and two neutrons. The fusion processes were primarily governed by the inherent properties of the strong nuclear force, which binds protons and neutrons together in the nucleus. Helium formation is favored in the hot, dense environment of the early universe because once two protons and two neutrons combine to form a helium nucleus, it is a more stable configuration compared to the individual protons and neutrons. Eventually, About 75% of the normal matter ended up in the form of hydrogen, while around 25% became helium. Only trace amounts of lithium and beryllium were produced due to their higher binding energies, which made their formation less favorable under the conditions of the early universe. This dominance of hydrogen and helium laid the groundwork for the evolution of stars and galaxies. These light elements acted as the primary fuel for stellar nucleosynthesis, enabling the formation of heavier elements within stars through processes that would unfold in the billions of years following the Big Bang. By understanding why hydrogen and helium were the predominant elements, scientists uncover crucial insights into the very nature of cosmic evolution and the building blocks of matter. The first elements, primarily hydrogen and helium, began to appear within a few minutes after the Big Bang, specifically during a process known as primordial nucleosynthesis. This process occurred roughly 3 to 20 minutes after the universe's explosive expansion began. During this short window of time, the universe cooled sufficiently to allow protons and neutrons to combine and form atomic nuclei. In the immediate aftermath of the Big Bang, the universe was an extremely hot and dense environment filled with fundamental particles like quarks, gluons, and electrons. As it expanded, the temperature decreased. When the universe cooled to about 10 billion degrees Celsius, conditions became suitable for nuclear interactions. Protons and neutrons, which had formed from quarks, began to fuse into simple nuclei, primarily hydrogen and helium. Once primordial nucleosynthesis concluded, the universe was predominantly composed of hydrogen, which made up about 75% of the total matter, while helium accounted for about 25%. Beyond hydrogen and helium, only trace amounts of other light elements, such as lithium and beryllium, were formed. This initial composition set the stage for the later formation of stars and galaxies. As the universe continued to expand and cool further, approximately 380,000 years after the Big Bang, electrons combined with the formed nuclei during a process called recombination, resulting in neutral atoms. This moment marked the release of the cosmic microwave background radiation, allowing photons to travel freely through space for the first time. Thus, while the fundamental elements emerged just minutes after the Big Bang, the formation of neutral atoms happened hundreds of thousands of years later, marking distinct phases in the early universe's evolution. Dark matter played an indirect yet crucial role in the formation of the first elements in the universe. While dark matter does not interact with electromagnetic forces and is therefore invisible and undetectable through conventional means, it exerts gravitational effects that influence the large-scale structure of the cosmos. This gravitational pull contributed to the process that led to the formation of clumps of matter, which were essential for the later development of stars and galaxies. After the Big Bang, the universe began expanding and cooling. Matter, primarily in the form of hydrogen and helium created during primordial nucleosynthesis, began to clump together under the influence of gravity. Dark matter, which is thought to make up around 26% of the universe's mass-energy content, played a significant role by providing the additional gravitational attraction needed for ordinary matter to coalesce. This created gravitational wells that facilitated the formation of the first structures in the universe. These clumps of matter eventually grew into halos of dark matter, within which regular matter could accumulate. Over time, as the density of matter increased, regions of gas became dense enough to collapse under their own gravity, leading to the creation of the first stars. Through nuclear fusion, these stars produced heavier elements, which would later become available for the formation of new stars and planets. In this sense, dark matter served as a scaffolding that shaped the early universe and allowed for the complex structures we observe today. While dark matter does not directly influence the formation of elements, its gravitational interactions are fundamental to the processes that lead to star formation and the subsequent synthesis of heavier elements in stellar interiors. Understanding dark matter's role provides essential context for the overall evolution of the universe and the origins of the elements that ultimately contribute to galaxies, solar systems, and life itself. To understand how the first molecules formed in the early universe, we must first look back to a time just after the Big Bang, approximately 13.8 billion years ago. In these initial moments, the universe was an incredibly hot and dense space where temperatures soared into the millions of degrees. During this period, energy was so intense that it prevented the formation of stable atoms. Instead, elementary particles, such as quarks, were constantly being created and annihilated. As the universe began to expand and cool, approximately 378,000 years after the Big Bang, a critical event known as recombination occurred. Electrons and protons combined to form neutral hydrogen atoms. This was the point when the universe became transparent, allowing light to travel freely. Nevertheless, hydrogen, being the simplest atom, was just the beginning. Over time, due to gravitational forces, these hydrogen atoms began to clump together, ultimately leading to the creation of the first stars and galaxies. Inside these early stars, nuclear fusion ignited, producing helium and traces of other light elements like lithium and beryllium. As these stars reached the end of their life cycles, they exploded in supernova, scattering their enriched guts, primarily hydrogen and helium, throughout the cosmos. It was during these cataclysmic events that more complex molecules began to coalesce, giving rise to the first molecular compounds. This process set the stage for the formation of stars and planets, as better-known molecules like water and carbon dioxide gradually emerged. The formation of the first molecules was not only a monumental step in chemical evolution, but also paved the way for the development of more complex structures, ultimately leading to the universe as we know it today. These early molecular formations played a crucial role in the emergence of life, the stars, and everything else in the cosmos, connecting the simplest particles to the intricate web of existence we see around us now. Interstellar dust plays a crucial role in the formation of complex molecules in space. Comprised of tiny particles mainly made up of carbon, silicate minerals, and ice, this dust exists in the vast regions between stars. Although it only makes up a small fraction of the total mass in the universe, it acts as a vital catalyst in the formation of more complex substances, marking a significant step in the chemistry of the cosmos. As the universe evolved, the first stars and galaxies formed from primordial hydrogen and helium. Over time, stars created heavier elements through nuclear fusion. When these stars died, they released their enriched material back into the interstellar medium, replenishing it with a variety of elements. Here, interstellar dust grains provided surfaces where atoms and molecules could accumulate and interact. This density of particles allows for chemical reactions to occur, where simpler molecules, such as hydrogen and carbon compounds, begin to bond and grow more complex. One of the most intriguing outcomes of this process involves the formation of the simplest organic compounds. These include amino acids, which are the building blocks of life. Observations of dense molecular clouds, regions rich in dust, have revealed an abundance of these organic molecules, showing that the seeds of life could very well originate far from Earth in the cold, dark expanses of space. The surface reactions facilitated by interstellar dust enable these complex molecules to form and even evolve into larger structures. The combination of stellar evolution and the influence of interstellar dust highlights a remarkable journey from simple atoms to complex molecules. This transformation not only contributes to the chemical richness of galaxies, but also serves as an essential link in the potential emergence of life, reminding us that the building blocks of existence are often forged in the quiet, dark regions between the stars. Detecting complex molecules in space is an exciting endeavor that combines advanced technology with astronomical observations. Scientists utilize a variety of methods to identify these intricate substances, each relying on the distinct ways molecules interact with light. One of the primary techniques involves spectroscopy, a powerful tool that analyzes the light emitted or absorbed by materials in space. When light passes through or interacts with a gas or dust cloud containing molecules, certain wavelengths of light are absorbed at specific frequencies, creating unique patterns known as absorption or emission lines. By carefully studying these spectral fingerprints, astronomers can determine which molecules are present. For example, water, carbon dioxide, and various organic compounds have unique signatures that reveal their presence in different environments, such as interstellar clouds, planets, or the atmospheres of distant exoplanets. Another approach involves utilizing radio telescopes to detect molecular emissions in the radio wavelength range. Many complex molecules emit radio signals when they transition between energy states. Observing these emissions offers insights into the physical and chemical conditions of celestial bodies, allowing scientists to uncover the types and quantities of molecules present. An example of this is the detection of methanol, which is commonly found in dense interstellar regions. Space missions and telescopes equipped with specialized instruments such as the Atacama Large Millimeter, Submillimeter Array, and the James Webb Space Telescope have significantly advanced our ability to detect complex molecules. These observations not only focus on well-known molecules, but also explore the presence of new and exotic compounds, contributing to our understanding of cosmic chemistry. Through these techniques, we continue to unlock the secrets of the universe, revealing the intricate tapestry of molecules that may ultimately connect to the origins of life itself. Interstellar space is rich in a surprising variety of complex molecules, some of which are quite intricate and significant in understanding cosmic chemistry. Among the most notable is a class of organic compounds known as polycyclic aromatic hydrocarbons. These molecules, composed of multiple fused benzene rings, are believed to form under high-energy conditions, such as those created by stellar processes. Their presence hints at the complexity of chemical reactions occurring in space and suggests that the building blocks of life may be more prevalent than previously thought. Another fascinating discovery is that of amino acids, the fundamental building blocks of proteins. Specific amino acids have been detected in meteorites as well as in gas and dust clouds throughout the galaxy. For instance, glycine, the simplest amino acid, has been identified in the molecular cloud known as Sagittarius B2. The presence of such compounds supports the idea that the basic ingredients for life might be widespread in the universe, potentially leading to the development of life as we know it. Sugars and alcohols have also been found in interstellar regions. Complex sugars such as ribose, a crucial component of RNA, have been detected in comet samples and gas clouds. Meanwhile, molecules like ethyl alcohol have been observed, underscoring the organic diversity present in space. These discoveries not only expand our understanding of molecular complexity in the universe, but also suggest pathways for how these substances might contribute to forming life. These complex molecules reveal a universe teeming with chemistry, bridging the gap between cosmic phenomena and the processes that may lead to life. As scientists continue to explore the vastness of space, they unveil the intricate connections between the elements produced in stars and the organic compounds that may one day explain the origins of life on Earth and beyond. The formation of organic molecules necessary for life in the universe is a fascinating process that begins with the simplest elements created shortly after the Big Bang. As the universe cooled, matter began to coalesce, and the primordial hydrogen and helium served as the foundational building blocks for more complex structures. Over time, the gravitational pull of incoming particles led to the formation of stars, which played a crucial role in producing the diverse array of elements we see today. Inside the hearts of stars, nuclear fusion occurs, combining hydrogen into helium and generating heavier elements such as carbon, nitrogen, and oxygen through subsequent fusion processes. When stars exhaust their nuclear fuel, they release these elements into the surrounding interstellar medium through powerful supernova explosions or stellar winds. This enriched cosmic dust and gas create a fertile environment for the synthesis of organic molecules. In the cooler, dense molecular clouds that follow, simple molecules like carbon dioxide, ammonia, and water can come together to form more complex organic compounds. These reactions often happen on the surfaces of interstellar dust grains, facilitating interactions that lead to the creation of molecules such as amino acids, nucleobases, and sugars. The ability of these dust grains to act as a catalyst is a key factor in the development of the rich chemical complexity required for life. Moreover, the dynamics of chemistry are also influenced by cosmic rays and ultraviolet radiation, which can provide the energy necessary to drive these reactions. As comets and asteroids form and carry these organic molecules through space, they may eventually collide with planets. This transport mechanism raises intriguing possibilities about how the essential ingredients for life might be delivered to planets like Earth, potentially sparking the chemical processes that led to the emergence of living organisms in various environments across the universe. Polycyclic aromatic hydrocarbons, often abbreviated as PAHs, play a significant role in our understanding of cosmic chemistry and the potential for life beyond Earth. These complex organic molecules consist of multiple fused benzene rings and are an abundant component of interstellar space. Their formation processes and widespread presence offer valuable insights into the chemical evolution of the universe. One of the primary significances of PAHs lies in their connection to star formation and the interstellar medium. These molecules can serve as a reservoir for carbon, which is a crucial element in the formation of more complex organic compounds. Their detection in dense molecular clouds suggests that PAHs are part of the ongoing processes that contribute to the chemical richness of the universe. Furthermore, as stars form from these clouds, PAHs can play a role in the radiative processes that influence the environment surrounding new stars, impacting the formation of additional molecules. PAHs are also intimately linked to the question of the origins of life. The very structure of PAH suggests that they can participate in various chemical reactions that lead to the creation of biologically relevant molecules. Some studies indicate that PAHs may be precursors to amino acids and other organic macromolecules that are essential for life. Their presence in the left-behind residue of ancient stars and galaxies raises intriguing possibilities about how complex chemistry might evolve into life-sustaining molecules. Moreover, detecting PAH in the atmospheres of distant exoplanets expands our understanding of the chemical processes beyond our solar system. Their identification can serve as a marker of organic chemistry occurring on other worlds, raising essential questions about the potential habitability of those environments. Polycyclic aromatic hydrocarbons are not just markers of cosmic processes. They may very well be a link between simple chemistry and the complexity required for life as we know it. Molecular clouds are dense regions of gas and dust in space, primarily composed of hydrogen molecules, but they also contain a variety of other elements and compounds. These clouds are crucial for the chemical evolution of the universe because they serve as the primary sites where complex molecules form and interact. The abundance of material within molecular clouds provides the necessary environment for numerous chemical reactions to occur, setting the stage for the emergence of stars, planets, and potentially life itself. As stars begin to form from the gravitational collapse of a portion of a molecular cloud, they trigger a cascade of chemical and physical processes. The intense heat and pressure within new stars lead to nuclear fusion, producing heavier elements that enrich the surrounding environment. When these stars reach the latter stages of their life cycles, they explode as supernovae, scattering newly formed elements like carbon, oxygen, and nitrogen back into space. This material then mixes with existing molecular clouds, enhancing their composition and facilitating the formation of even more complex molecules. The interactions that occur within molecular clouds are particularly interesting because they allow for the synthesis of a variety of organic molecules. Reactions occurring on dust grains serve as catalysts, enabling simpler molecules to bond and form more intricate structures. For instance, amino acids, sugars, and other organic compounds have been detected in these clouds. The presence of these complex molecules hints at the potential for the building blocks of life to exist throughout the universe. Molecular clouds are not only essential for the formation of stars and the chemical building blocks necessary for life, but also play a role in the broader cosmic cycle. As stars are born and die, they contribute to the ever-evolving chemical landscape of galaxies. This continuous process creates an intricate web of chemistry that connects different phases of stellar life and shapes the composition of future generations of stars and planetary systems. In this way, molecular clouds are a fundamental component of the ongoing story of chemical evolution in the universe. The formation of the first stars from primordial gas took place within a few 100 million years after the Big Bang, during a period often referred to as the cosmic dawn, or the era of reionization. In this early universe, hydrogen and helium were the predominant elements, and the gravitational influence of dark matter played a crucial role in the process. The gravitational collapse of dense regions within the primordial gas allowed for the formation of the first stars, marking a seminal event in cosmic history. As regions of dark matter began to clump together under their own gravity, they created gravitational wells that affected the surrounding gas. This gas, primarily composed of hydrogen and helium, fell into these wells, increasing density and temperature in those areas. These gravitational collapses occurred over time as the universe expanded and cooled, making it possible for regions with slightly higher densities to begin their formation processes. As the gas accumulated, it became increasingly dense and formed what are known as protostars. In the cores of these collapsing gas clouds, the temperature and pressure rose significantly due to gravitational forces. When the core temperatures reached around 10 million degrees Celsius, nuclear fusion reactions began to occur, converting hydrogen into helium, the vital process that fuels stars. This marked the transition from a protostar to a fully formed star. Meanwhile, the surrounding gas continued to be drawn in, allowing the star to grow larger and more luminous. The first stars, often referred to as population 3 stars, were significantly different from the stars we see today. They were likely much more massive and hotter, composed almost entirely of hydrogen and helium without the heavier elements produced in later generations. This initial generation of stars played a pivotal role in the evolution of the universe. When they reached the end of their life cycles, they exploded as supernovae, releasing energy and synthesizing heavier elements that enrich the interstellar medium. This cycle of star formation and death helped set the stage for subsequent generations of stars and the diverse chemical compositions we observe in the universe today. The first generation of stars, known as population 3 stars, exhibited several distinctive characteristics that set them apart from later generations of stars. Formed from primordial gas composed mostly of hydrogen and helium, these stars were crucial in shaping the evolution of the universe. One of their most notable features was their massive size. Population 3 stars were likely much more massive than the average stars we see today, often reaching masses hundreds of times greater than our Sun. Due to their immense mass, these early stars burned through their nuclear fuel at a rapid pace, leading to very short lifespans, typically on the order of a few million years. This contrasts significantly with more recent stars, which can exist for billions of years. The high temperatures and pressures within these massive stars resulted in vigorous fusion processes, primarily converting hydrogen into helium and producing significant quantities of radiation and energy. Another striking characteristic of population 3 stars was their lack of heavy elements. Formed from the primordial hydrogen and helium created during primordial nucleosynthesis, these stars had not yet undergone the nucleosynthesis processes that produce heavier elements found in later generations. Consequently, when these stars reached the end of their life cycles, they exploded as supernovae, ejecting primarily hydrogen and helium, along with newly forged heavier elements like carbon, oxygen, and nitrogen into the surrounding interstellar medium. This enrichment allowed for the formation of subsequent generations of stars, which incorporated these heavier elements. The environments in which these first stars formed were also significant. They emerged in regions dominated by dark matter, where gravitational forces facilitated the accumulation of gas. The immense energy output of these stars influenced their surroundings, causing heating and ionization of the interstellar medium, key processes in the cosmic reionization era that shaped the structure of the early universe. The characteristics of population 3 stars laid the groundwork for the diverse array of stars, planets, and galaxies that would follow in the unfolding tapestry of cosmic evolution. Studying the earliest galaxies in the universe is a complex endeavor that relies on a combination of advanced observational techniques and theoretical models. Astronomers utilize powerful telescopes capable of detecting faint light from distant objects, often looking back in time to see galaxies as they appeared billions of years ago. Since light from these distant galaxies takes a significant amount of time to reach us, observing them provides a glimpse into a younger universe. One primary method involves using infrared observations. Most of the earliest galaxies emitted light primarily in the ultraviolet spectrum, but as the universe expanded, this light was redshifted to longer wavelengths, including the infrared. Telescopes equipped with infrared capabilities, such as the Hubble Space Telescope and the more recent James Webb Space Telescope, can detect this redshifted light, revealing the characteristics of these ancient galaxies. These instruments cover a wide range of wavelengths, allowing researchers to analyze the formation and evolution of stars within these galaxies. Additionally, gravitational lensing plays a crucial role in studying early galaxies. This phenomenon occurs when a massive object, such as a galaxy or cluster of galaxies, is positioned between an observer and a more distant galaxy. The gravitational field of the foreground object bends the light from the distant galaxy, effectively magnifying and distorting it. Researchers can use this effect to uncover faint and distant galaxies that would otherwise remain hidden due to their weak light. Theoretical simulations and models also contribute significantly to our understanding of early galaxies. By combining observations with computational simulations, scientists can simulate the formation and evolution of galaxies under various conditions. These simulations help interpret data and make predictions about what early galaxies might have looked like based on the physical laws governing gravity, gas dynamics, and star formation. Overall, the study of the earliest galaxies combines observational prowess with theoretical insights. As technology advances, astronomers are continually refining their techniques, allowing deeper insights into the formation and evolution of galaxies in the early universe. The exploration of these ancient structures is pivotal for understanding our cosmic history and the processes that gave rise to the universe as we know it today. The cosmic web is a vast and intricate structure that represents the large-scale arrangement of matter in the universe. It resembles a fine tapestry woven from the threads of galaxies, galaxy clusters, and dark matter, forming a complex network. This network comprises filaments and voids, where filaments are the dense regions of galaxy clusters and groups that connect to other filaments, while voids are the relatively empty spaces between these structures. The cosmic web is crucial for understanding the distribution of galaxies and the evolution of the universe. The development of the cosmic web can be traced back to the physics of the early universe. After the Big Bang, matter was distributed nearly uniformly, but slight density fluctuations existed due to quantum fluctuations. As the universe expanded and cooled, these small variations in density became amplified through gravitational attraction, allowing matter to clump together over time. Dark matter played an essential role in this process due to its gravitational influence. Although invisible, it constitutes a significant portion of the universe's mass and facilitated the clumping of both dark and ordinary matter. As the universe continued to evolve, regions of higher density attracted more matter, forming the first star clusters and galaxies. Over time, these structures merged and interacted through gravitational forces, creating larger clusters of galaxies and defining the original filaments and voids characteristic of the cosmic web. The growth of these structures was influenced by the expansion of the universe, which also affected how matter interacted across great distances. Today, the cosmic web serves as a vital framework through which astronomers can study the distribution of galaxies and the flow of cosmic matter. Observations of this network help researchers understand the formation and evolution of galaxies as they trace back to the earlier stages of the universe. Various survey projects, such as the Sloan Digital Sky Survey, provide data on the large-scale distribution of galaxies, enabling scientists to paint a picture of the cosmic web's structure and dynamics over cosmic time. Studying the cosmic web is fundamental to understanding not only how our universe is organized, but also the physical processes driving cosmic evolution. Supermassive black holes are essential to our understanding of galaxy formation and evolution, with their presence intricately linked to the formation of galaxies themselves. These black holes, which can have masses ranging from millions to billions of times that of the Sun, are commonly found at the centers of most large galaxies, including our own Milky Way. Their formation likely occurs concurrently with the galaxies they inhabit, and they influence galactic dynamics and growth in profound ways. The prevailing theory suggests that supermassive black holes originated from the direct collapse of massive gas clouds in the early universe or through the merging of smaller black holes. As these black holes formed, they began to exert a strong gravitational influence on their surrounding environment. This gravitational pull can affect the dynamics of stars and gas within the galaxy, leading to the formation of a central bulge and impacting star formation rates. In this sense, supermassive black holes may help dictate the structure and content of the galaxies that host them. Moreover, feedback mechanisms associated with supermassive black holes can profoundly influence galaxy evolution. As these black holes accrete matter, they release substantial amounts of energy in the form of radiation, which can heat up the surrounding gas and inhibit further star formation. This feedback process can regulate star formation rates within the galaxy, contributing to the overall balance between black hole growth and the formation of new stars. When a black hole's activity is particularly intense, it can lead to phenomena such as quasars, where energy emissions can outshine entire galaxies. Additionally, the relationship between supermassive black holes and galaxies is observed statistically. The mass of a supermassive black hole is closely correlated with the mass and properties of the host galaxy's bulge. This correlation suggests a co-evolution, where feedback from black holes shapes their galaxies, and vice versa. Understanding this interconnected relationship provides valuable insights into galactic formation and evolution, revealing how supermassive black holes are not merely passive occupants, but active participants in the processes that shape the cosmos. This interplay offers a deeper comprehension of the cosmic tapestry, highlighting the complex relationship between structure, dynamics, and evolution at both galactic and cosmic scales. Dark energy plays a pivotal role in the expansion of the universe, acting as a mysterious force that contributes to the observed accelerated expansion. While the universe has been expanding since the Big Bang, the discovery that this expansion is accelerating was one of the most groundbreaking revelations in cosmology. This acceleration suggests that something beyond ordinary matter and radiation is influencing the dynamics of the cosmos, and that something is dark energy. About 70% of the universe is believed to be comprised of dark energy. Its nature remains one of the biggest mysteries in modern physics, but it is thought to exhibit a repulsive gravitational effect, counteracting the attractive force of gravity from matter. As the universe expands, the density of ordinary matter decreases. However, dark energy appears to have a constant density, meaning that as the universe grows larger, its influence grows more significant in comparison to the diminishing density of matter. This results in the increased rate of expansion currently observed. The concept of dark energy is often associated with the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity, which he initially proposed to allow for a static universe. After the observation of an expanding universe, he retracted this idea, But with the discovery of the universe's accelerated expansion in the late 20th century, the cosmological constant was revived as a potential explanation for dark energy. This constant energy density provides a simple model, but various alternative theories exist, including dynamic forms of dark energy known as quintessence. Understanding dark energy is crucial for cosmologists, as it influences the fate of the universe. If dark energy continues to dominate over gravitational forces, it could lead to scenarios where galaxies are driven apart at increasing speeds, ultimately resulting in a universe that expands indefinitely without ever collapsing. This has profound implications for the eventual fate of celestial structures and the universe itself, making the study of dark energy a central focus in modern cosmology and theoretical physics. As researchers work to unveil the true nature of dark energy, they continue to explore its profound impact on the universe's evolution and ultimate destiny. Stars form from interstellar gas and dust through a process that begins within enormous clouds known as molecular clouds, which are primarily composed of hydrogen molecules, along with other gases and dust particles. These clouds are cold, dense regions of space, providing the necessary conditions for star formation to occur. The initial step in the process involves the gravitational collapse of a portion of these clouds, triggered by various factors such as shock waves from nearby supernova explosions or collisions with other clouds. As an area within a molecular cloud begins to collapse under its own gravity, it becomes denser, and the temperature rises. This core of material forms what is called a protostar. The gravitational forces continue to pull in surrounding gas and dust, increasing the mass of the protostar and causing it to heat up further. Throughout this stage, matter falls toward the protostar, often forming a rotating disk around it, which helps channel additional material into the growing star. As the temperature and pressure in the core of the protostar increase, eventually reaching millions of degrees Celsius, nuclear fusion reactions are initiated. These reactions convert hydrogen into helium, releasing energy in the process. When the energy output from fusion balances the gravitational forces trying to collapse the star, the protostar becomes a main sequence star, entering a stable phase of its life. This marks the transition from a protostar to a fully formed star. The surrounding material in the rotating disk often leads to the formation of planets, moons, and other celestial objects as it coalesces through similar gravitational processes. Thus, the formation of stars not only creates new celestial bodies, but also plays a significant role in shaping planetary systems. The intricate dance of gas, dust, and gravity results in the birth of stars, illuminating the universe and generating the heavier elements necessary for life, fueling the process of cosmic evolution. Nuclear fusion is the powerful process that fuels stars, including our own sun. At the core of a star, extreme temperatures and pressures create an environment where hydrogen nuclei can overcome their natural repulsion to collide and fuse together. This fusion process converts hydrogen into helium, releasing a tremendous amount of energy in the form of light and heat. The conditions required for fusion mean that temperatures must reach millions of degrees Celsius and pressures must be incredibly high. At these temperatures, electrons are stripped away from atoms, creating a hot plasma of free protons and nuclei. When these particles collide with enough energy, they combine to form a heavier nucleus, which in turn releases energy due to the mass-energy equivalence principle. This principle states that a small amount of the mass of the reacting particles is converted into energy. As stars age, they exhaust their hydrogen fuel and may begin to fuse helium into heavier elements such as carbon and oxygen. This progression can create a chain reaction of fusion, producing elements up to iron in the cores of massive stars. Once a star runs out of fuel, the lack of fusion leads to changes in its structure, potentially culminating in spectacular events like supernovae, which can disperse these newly formed elements into space. Thus, the process of nuclear fusion is not just the key to a star's life, but also a vital mechanism for enriching the universe with the elements necessary for planets and, ultimately, life itself. Stars produce heavier elements through a series of nuclear fusion processes that occur during their life cycle, particularly in the later stages. Initially, stars begin by fusing hydrogen into helium in their cores. As they exhaust their hydrogen supply, the core contracts and heats up, allowing them to fuse helium into heavier nuclei, such as carbon and oxygen. This process typically happens in stars that are at least several times the mass of the Sun. When the core temperature reaches around 100 million degrees Celsius, helium nuclei can collide with enough energy to undergo fusion, creating heavier elements through a series of nuclear reactions. For example, 3 helium nuclei can combine to form carbon, and through further collisions, carbon can be fused into even heavier elements like neon and magnesium. This process, known as stellar nucleosynthesis, occurs in the core and sometimes in surrounding layers, depending on the star's mass. For the most massive stars, once the core has built up elements like iron, fusion reactions can no longer release energy, as fusing heavier elements consumes energy instead. When the core becomes predominantly iron, it can no longer support the layers of the star above it, leading to a catastrophic collapse. This collapse triggers a supernova explosion, which spews these newly formed elements into the surrounding space. The environment of a supernova provides the extreme conditions necessary for rapid neutron capture, a process known as the R process. This creates even heavier elements like gold and uranium. Consequently, the material ejected from supernovae enriches the interstellar medium, allowing future generations of stars to form from this elemental mix, thus ensuring a continual cycle of element formation throughout the universe. When a star runs out of fuel, it undergoes profound changes that can lead to various dramatic outcomes, depending on its initial mass. For smaller stars, like those similar in size to the Sun, the end of nuclear fusion begins a process of instability. As hydrogen is depleted in the core contracts under gravity while the outer layers expand and cool, transforming the star into a red giant. During this phase, the star can temporarily fuse helium into heavier elements. Eventually, the core contracts further, and the outer layers are expelled into space, forming a beautiful nebula. What remains of the core becomes a white dwarf, an incredibly dense object no longer undergoing fusion. The white dwarf will gradually cool over billions of years, eventually fading from view. In contrast, massive stars experience a more violent end when they exhaust their nuclear fuel. After going through multiple stages of fusion, the core becomes primarily iron, which does not produce energy through fusion. At this point, the core cannot support the weight of the star above it, leading to a catastrophic collapse. This collapse creates an immense shockwave that triggers a supernova explosion, blasting the outer layers of the star into the cosmos. The remnants of the supernova can result in either a neutron star or a black hole, depending on the mass of the original star. A neutron star is an incredibly dense object composed mainly of neutrons, while a black hole forms if the core's mass exceeds a specific limit, creating a gravitational pull so strong that not even light can escape. Thus, the fate of a star is intricately tied to its mass, with those born as massive giants ending their lives in spectacular and violent fashion, while smaller stars settle into quieter, albeit still fascinating, conclusions. Supernovae play a critical role in the evolution of the universe by distributing heavy elements throughout the cosmos and influencing the formation of new stellar systems. When a massive star explodes as a supernova, it ejects vast amounts of material into the interstellar medium. This material is rich in elements created during the star's life, as well as those forged during the explosive event itself, such as gold, uranium, and various other heavy elements. The energy released in a supernova is immense, providing shock waves that compress surrounding gas and dust. This compression can trigger the collapse of nearby molecular clouds, leading to the birth of new stars. With the mixture of elements spread by the supernova, the new stars that form can incorporate a variety of heavier elements, enriching the chemical composition of future generations of stars and planets. Thus, supernovae are vital for the gradual build-up of complexity in the universe. Moreover, the explosion of a supernova can influence the dynamics of galaxies. By injecting energy and mass into the interstellar medium, the ejected material contributes to the processes of star formation within galaxies. In this way, supernovae act as drivers of galactic evolution, shaping the structure and composition of galaxies over time. Additionally, studying supernova allows astronomers to gain insights into cosmic distances and the expansion of the universe, particularly through observations of type Ia supernovae, which serve as reliable standard candles. These insights have profound implications for understanding the underlying mechanics of the universe and its ultimate fate. Thus, supernovae are not just explosive events. They are fundamental processes that facilitate the continuous cycle of stellar birth, evolution, and death, contributing significantly to the rich tapestry of the universe. Neutron stars are incredibly dense remnants of massive stars that have undergone supernova explosions. When a star that is at least 8 times more massive than the Sun exhausts its nuclear fuel, it can no longer support the weight of the outer layers, leading to a collapse of the core. This collapse happens in a fraction of a second, creating conditions of extreme density and pressure. During the core collapse, protons and electrons combine to form neutrons, resulting in a neutron star primarily composed of densely packed neutrons. The density of a neutron star is astonishing. Just a sugar cube-sized amount of this material would weigh about the same as all of humanity combined. This extreme density is balanced by the forces of quantum physics, particularly neutron degeneracy pressure, which arises when neutrons are packed closely together and prevents further collapse. Neutron stars typically have a radius of around 10 kilometers, making them incredibly compact. They possess strong magnetic fields and can rotate at incredibly high speeds, with some spinning several times per second. If a neutron star's magnetic field is tilted relative to its rotation, it can emit beams of radiation, making it detectable as a pulsar. These pulsars sweep across the sky like lighthouses, providing valuable data to scientists studying the properties of neutron stars and the fundamental laws of physics. The formation of neutron stars is a crucial step in the evolution of the universe, as they play a significant role in the synthesis of heavy elements through processes such as neutron capture during the supernova explosion. As remnants of the most massive stars, neutron stars also represent one of the endpoints of stellar evolution, bridging the gap between conventional stars and exotic objects like black holes. Their existence raises intriguing questions about the nature of matter and the forces that govern the universe. Planet formation around stars occurs in a process called accretion, which takes place in the protoplanetary disk, a rotating disk of gas and dust that surrounds a newborn star. In the early stages of a star's formation, gravitational forces pull together material from the surrounding molecular cloud, creating the dense core that ultimately becomes a star. Meanwhile, the leftover gas and dust spread out into a disk structure, providing the raw ingredients for planet formation. Within this protoplanetary disk, tiny particles of dust and ice collide and stick together, gradually forming larger structures called planetesimals. This initial stage of growth can take several million years. As these planetesimals continue to collide and merge, they form larger bodies called protoplanets. Through a combination of gravitational attraction and continued collisions, these protoplanets accumulate more mass, eventually growing large enough to become full-fledged planets. The location within the protoplanetary disk significantly influences the types of planets that form. In the hotter, inner regions near the star, rocky planets like Earth and Mars develop as the heat causes lighter materials to vaporize, leaving behind metals and silicates. In contrast, the colder outer regions allow for the formation of gas giants such as Jupiter and Saturn, where hydrogen and helium can accumulate along with other lighter compounds like ammonia and methane. Over time, as the disk dissipates, due in part to radiation from the star and other dynamical processes, the planets stabilize in their orbits. Some may collide with each other, while others might be flung out of the system entirely. The remaining planets settle into their positions, leading to the diverse array of planetary systems we observe across the galaxy today, shaped by the unique conditions of their respective protoplanetary disks and the dynamics of their formation processes. The current theory of the formation of our solar system is known as the nebula hypothesis. It suggests that our solar system formed approximately 4.6 billion years ago from a giant molecular cloud composed of gas and dust. This cloud, primarily made up of hydrogen and helium, experienced a gravitational collapse, possibly triggered by nearby supernovae or other cosmic events, leading to the formation of a spinning protoplanetary disk. As the cloud collapsed under its own gravity, most of the material migrated towards the center, creating a dense region that eventually became the Sun. The remaining gas and dust spread out into a rotating disk around the newborn star. Within this protoplanetary disk, particles began to stick together, forming larger bodies known as planetesimals. Through a process of collisional accumulation, these planetesimals gradually coalesced into protoplanets over millions of years. The temperature and pressure gradients within the disk played a vital role in determining the types of bodies that formed at various distances from the Sun. In the hotter inner regions, where temperatures were higher, rocky planets such as Earth and Mars formed. Meanwhile, in the cooler outer regions, gas giants like Jupiter and Saturn developed, attracting large amounts of hydrogen and helium due to their substantial gravity. The icy bodies beyond Neptune contributed to the formation of smaller, icy bodies, which later became the dwarf planets and comets we observe today. As the Sun ignited nuclear fusion, radiation and solar wind cleared away much of the remaining gas in the disk, halting the planet formation process. The resulting configuration set the orbits of the planets and smaller bodies, leading to the structured solar system we know now. This theory has evolved with advancements in observational astronomy and planetary science, providing insights into our solar past and the broader mechanisms behind the formation of planetary systems across the universe. Exoplanets, or planets outside our solar system, are incredibly common in the universe. Since the first confirmed discovery of an exoplanet in 1995, astronomers have identified thousands of these distant worlds, and the number continues to grow rapidly. Current estimates suggest that there may be more exoplanets than stars in our galaxy, which contains around 100 billion stars. This implication leads to the conclusion that there could be as many as 100 billion planets in just the Milky Way. Recent studies based on data from telescopes, such as the Kepler Space Telescope, indicate that exoplanets are likely to exist in a wide variety of types and orbits. Many of these planets are situated within their star's habitable zone, the region where conditions might allow for liquid water to exist, which is fundamental for life as we know it. In fact, a significant percentage of stars have Earth-sized planets in their habitable zones, raising intriguing possibilities about the prevalence of potentially habitable worlds. The discoveries of exoplanets have revealed a diverse array of planetary systems, from those with multiple planets orbiting close to their stars to systems harboring gas giants far from their suns. The variety of formation processes and environmental conditions suggests that planet formation is a common outcome from star formation across the universe. As technology and observational methods continue to improve, such as the launch of the James Webb Space Telescope, the search for exoplanets and the study of their atmospheres and compositions will likely provide further insights into their abundance and the potential for life beyond our solar system, deepening our understanding of the cosmos. Several key conditions must be met for rocky planets, often referred to as terrestrial planets, to form within a protoplanetary disk. First and foremost, the presence of solid materials is crucial. These planets typically form in the inner regions of a disk, where temperatures are higher, allowing for heavier elements like metals and silicates to condense into solid particles. This region is often warmer than the outer areas, where gaseous compounds dominate, leading to a stark contrast in the types of planets that can form. The accretion process, where dust and ice particles collide and stick together, is paramount for building larger bodies. As these solid particles grow into planetesimals, gravitational forces become significant, allowing them to attract even more material. The rate of collisions and the presence of enough solid material determine the efficiency and speed of this accretion process. If there is an adequate quantity of solid material in the right region of the disk, it facilitates the formation of substantial protoplanets. Additionally, the dynamics of the protoplanetary disk influence rocky planet formation. The disk needs to be stable enough to allow the particle accretion process to occur over time, but also dynamic enough to promote the initial collisions. Turbulence within the disk can assist in concentrating solid materials and fostering interactions between particles. Finally, the environmental conditions surrounding the forming planet, such as the star's distance and the presence of volatile substances, affect the outcome. For example, a rocky planet must be properly positioned within the habitable zone, where temperatures allow for the presence of liquid water, although this is not crucial for the initial formation. Overall, the conditions in a protoplanetary disk are intricately linked, influencing the emergence of rocky planets and setting the stage for the diversity we see in planetary systems. Gas giants and ice giants form through processes similar to those of rocky planets, but the conditions and materials involved differ significantly. Both types of giants typically form in the colder outer regions of a protoplanetary disk, where lower temperatures allow for the presence of volatile compounds such as hydrogen, helium, water, ammonia, and methane to condense into solid and liquid forms. The formation of gas giants such as Jupiter and Saturn begins similarly to rocky planets, with the accretion of solid materials into planetesimals. Once a core forms with sufficient mass, likely several times the mass of Earth, gravitational forces play a crucial role. A massive core can attract and retain significant amounts of gas from the surrounding protoplanetary disk. This ability to draw in gas is essential for the rapid accumulation of a thick atmosphere. In this way, gas giants can gather vast envelopes of hydrogen and helium before the gas in the disk dissipates due to the stellar radiation and wind from the young star. Ice giants like Uranus and Neptune are somewhat smaller than gas giants and have a different composition that reflects their formation history. Their cores likely also form in a manner similar to gas giants, but they accumulate less gaseous material relative to their solid core mass. The outer atmospheres of ice giants consist of a larger proportion of icy and rock materials compared to the primarily hydrogen and helium composition of gas giants. This unique blend gives ice giants their distinct characteristics and can be attributed to their formation occurring in regions where conditions favored the accumulation of volatiles. Both types of giants influence their surrounding environments, particularly during the early stages of their formation. Their strong gravitational fields can affect the orbits of smaller bodies, potentially pushing them into the inner parts of the solar system or capturing others as moons. The formation of gas giants and ice giants is deeply tied to their initial location within the protoplanetary disk, the materials available, and the timing of gas retention, resulting in the diverse planetary systems we observe today. Comets and asteroids are integral to the process of planetary system formation, providing crucial material and insights into the building blocks of planets. These small celestial bodies are remnants from the early solar system and offer valuable information about the conditions that prevailed during its formation. Asteroids primarily form in the warmer inner regions of the protoplanetary disk, where rock and metal can coalesce. In contrast, comets originate further out, in the colder regions where ice and gas dominate, forming a mixture of ices, dust, and rocky materials. During the process of planet formation, asteroids and comets serve as important sources of materials for growing planets. As larger bodies, such as protoplanets, formed through the accretion of solid particles in the protoplanetary disk. They could collide with and incorporate asteroids, further enriching their composition. Such collisions could also lead to the formation of new moons and contribute to the geological evolution of the planets, as impacts can generate heat and influence atmospheric conditions. Comets, on the other hand, play a significant role in delivering water and organic materials to rocky planets like Earth. The impact of comets during the late stages of the solar system's formation might have contributed to the presence of liquid water on some planets, helping to establish conditions suitable for life. These icy bodies can transport essential compounds, including simple organic molecules, which are considered critical for the origin of life. Furthermore, the study of comets and asteroids can reveal important insights into the early solar system's conditions and the processes involved in planet formation. Their relatively unchanged compositions act as time capsules, allowing scientists to analyze materials that have remained since the solar system's infancy. Thus, comets and asteroids not only contribute essential materials to the formation of planets, but also play a key role in understanding the history of our solar system and the potential for life beyond Earth. Earth formed approximately 4.6 billion years ago from the material in the solar nebula, a giant rotating disk of gas and dust that surrounded the young sun. This process began shortly after the sun ignited and created its own gravitational pull. The circumstellar disk contained remnants of earlier stars, enriched with heavier elements produced through stellar evolution, making it a fertile ground for planet formation. As the solar nebula began to cool, tiny particles of dust and ice began to collide and stick together, forming larger and larger bodies known as planetesimals. These planetesimals, ranging from meters to kilometers in size, accumulated within the protoplanetary disk. Over millions of years, these bodies grew through a process called accretion, where they attracted more material due to their gravitational forces. Larger bodies continued to collide and merge, creating protoplanets. One of these protoplanets eventually grew large enough to become Earth. During this formative period, additional collisions occurred frequently, leading to the release of energy and heat, allowing the planet to remain molten for an extended time. This heat resulted in the differentiation of Earth's interior, with denser materials sinking to form the core while lighter materials rose to create the mantle and crust. Around 4.5 billion years ago, a significant event shaped Earth even further: the hypothesized impact with a Mars-sized body called Theia. This colossal collision sent debris into orbit around Earth, eventually coalescing to form the Moon. The aftermath of this collision and the continued bombardment by leftover planetesimals played a crucial role in shaping Earth's surface. The environment eventually stabilized, allowing for the development of oceans and the early atmosphere, making Earth a dynamic and evolving planet ready for the emergence of life. The process of Earth's differentiation into core, mantle, and crust occurred during its early molten phase shortly after formation. As the planet formed through the accretion of material, the energy generated from collisions, radioactive decay, and gravitational compression caused temperatures to rise significantly. This heat kept Earth in a molten state, allowing materials to move and separate based on their densities. As Earth continued to accumulate mass, denser materials, primarily metals like iron and nickel, began to sink towards the center of the planet due to gravity. This movement created a layered structure, with the most dense materials forming the core. The core eventually became composed primarily of iron, and is conjectured to have both a solid inner core and a liquid outer core, the latter contributing to Earth's magnetic field through its dynamic movements. Conversely, lighter materials, such as silicates and other less dense minerals, rose to the surface. These materials contributed to the formation of the mantle and crust. The mantle, situated above the core, consists of semi-solid rock that can flow slowly over geological timescales. This layer plays a critical role in tectonic processes like plate movement. The uppermost part of the mantle, along with the rigid surface layer, forms the crust, which is the thin outer shell of the Earth where we find continents and ocean floors. The differentiation process not only established the planet's layered structure, but also significantly influenced its geological and atmospheric evolution. As the core formed, it generated heat and contributed to the early magnetic field, while the crust and mantle continued to evolve through volcanic activity, plate tectonics, and erosion. The overall differentiation laid the foundation for Earth's dynamic and complex geological systems, shaping the environment that eventually allowed life to emerge. The origins of Earth's water are thought to be a combination of internal processes and extraterrestrial sources. One primary theory suggests that some of the water on Earth may have originated from the volcanic outgassing of water vapor and other gases during the planet's formation. As Earth cooled after its formation, this water vapor could have condensed to form liquid water, contributing to the earliest bodies of water, including oceans. However, a significant portion of Earth's water is believed to have come from external sources, particularly from the delivery of water-rich materials like comets and other icy bodies during the late heavy bombardment phase about 4 billion years ago. During this chaotic period, numerous asteroids, comets, and planetesimals collided with Earth, bringing with them volatile compounds, including water in the form of ice. This impact delivery could have provided the necessary layers of water that eventually filled the oceans. In addition to comets, some theories also point to a group of water-rich asteroids known as carbonaceous chondrites, which may have impacted Earth and contributed to its water inventory. These asteroids are rich in both water and organic molecules, which further supports the idea that Earth received essential building blocks for life via these celestial bodies. Over time, these processes allowed Earth to accumulate significant amounts of water, creating conditions favorable for the development of life. The ongoing interactions among water, rocks, and the atmosphere have continued to support life and shape Earth's surface, making water a vital component of our planet's identity and ecology. The late heavy bombardment refers to a period roughly 4 billion years ago when the inner solar system, including Earth, experienced a dramatic increase in the frequency of asteroid and comet impacts. This intense phase of bombardment is believed to have lasted for several hundred million years and is primarily understood through the study of the lunar surface, where many impact craters remain well preserved due to the Moon's lack of atmosphere and geological activity. The effects of the late heavy bombardment on Earth were significant and multifaceted. Firstly, the bombardment likely caused substantial geological changes, including the creation of craters, volcanic activity, and the alteration of the planet's surface landscape. The impacts delivered immense energy, leading to the melting of surface materials and potentially triggering large-scale volcanic eruptions. These eruptions could have released gases into the atmosphere, influencing Earth's climate and environment. Perhaps most importantly, the late heavy bombardment is thought to have played a crucial role in the delivery of water and organic materials to Earth. Many of the impacting bodies were likely water-rich asteroids and comets, which may have contributed to the formation of Earth's oceans. The impact events could have also provided vital organic compounds, serving as building blocks for the origins of life. While the bombardment would have made the Earth's surface inhospitable to life for a time, it is also theorized that the subsequent cooling and stabilizing of the planet, along with the formation of oceans, created the necessary conditions for life to emerge. The late heavy bombardment thus represents a critical period in Earth's early history, reshaping the planet and potentially laying the groundwork for the rise of life in the eons to come. Earth's atmosphere formed shortly after our planet itself coalesced about 4.5 billion years ago. Initially, the young Earth was a molten mass, and as it cooled, gases such as water vapor, carbon dioxide, ammonia, and methane began to escape from the planet's interior. This outgassing process, primarily driven by volcanic activity, contributed to the early atmosphere that enveloped the planet. However, the conditions on Earth during this time were extremely inhospitable, characterized by intense heat and little to no oxygen. As Earth continued to cool, water vapor began to condense, forming oceans. These bodies of water played a crucial role in the evolution of the atmosphere. Over millions of years, the oceans absorbed significant amounts of carbon dioxide, which helped to moderate the greenhouse effect and cooled the planet further. At the same time, photosynthetic organisms emerged, such as cyanobacteria, which began to produce oxygen as a byproduct of photosynthesis. This marked a turning point in Earth's atmospheric evolution. The Great Oxygenation Event, which occurred around 2.4 billion years ago, transformed the atmosphere dramatically. Oxygen levels increased significantly, fundamentally changing the composition of the atmosphere and allowing for the emergence of aerobic life forms. This surge in oxygen not only shaped biological evolution, but also contributed to the formation of the ozone layer, which protects the surface from harmful ultraviolet radiation. Over time, Earth's atmosphere has continued to evolve due to geological, biological, and anthropogenic influences. The present-day atmosphere is composed mainly of nitrogen and oxygen, with trace amounts of other gases. Human activities, particularly the burning of fossil fuels, are now impacting atmospheric composition, leading to concerns about climate change and environmental degradation. Understanding the formation and evolution of Earth's atmosphere is crucial, not just for grasping our planet's history, but also for predicting its future. Evidence for early plate tectonics on Earth comes from a multitude of sources, including geological formations, the distribution of fossils, and the patterns of ancient rock types. One of the strongest indicators is the presence of distinct geological features that align with the movement of tectonic plates. For instance, the matching coastlines of continents such as Africa and South America suggest they were once part of a larger landmass before drifting apart. This idea, known as continental drift, laid the groundwork for the theory of plate tectonics. Additionally, the arrangement and age of rocks found in mountain ranges can provide vital clues. The Appalachian Mountains in North America and the Caledonian Mountains in Scotland share geological similarities, indicating that these regions were once connected. The presence of ancient volcanic rocks and the patterns of seafloor spreading also imply that the process of plate tectonics has been ongoing for billions of years. Scientists have found rocks that form along mid-ocean ridges, showing that new crust is created as tectonic plates move apart. Fossil evidence also plays a significant role in supporting early plate tectonics. Fossils of the same species have been discovered on continents that are now widely separated, suggesting that these continents were once joined together. For example, fossils of the reptile Mesosaurus have been discovered in both South America and Africa, reinforcing the notion of continental cohesion in the past. Moreover, the analysis of ancient rocks, particularly those dating between 3 billion and 2 billion years ago, reveals signs of extensive tectonic activity. Structures such as subduction zones, where one tectonic plate moves under another, suggest that even in the early Earth, dynamic processes were at play. The geological history recorded in rocks, alongside the distribution of life and continents, converges to create a strong case for the existence of early plate tectonics, emphasizing how these forces have shaped our planet over geological time. Current theories on how life began on Earth largely fall into several distinct categories, each proposing different mechanisms and environments that could have facilitated the emergence of living organisms. One of the most prominent theories is the primordial soup hypothesis. This idea suggests that life began in a watery environment filled with organic compounds. These compounds may have formed from simpler molecules, such as methane and ammonia, through various energy sources like lightning or ultraviolet radiation. Experiments simulating early Earth conditions, like the famous Miller-Urey experiment, have demonstrated that amino acids, the building blocks of proteins, can form under these circumstances. Another well-supported theory is the concept of hydrothermal vent environments. Proponents argue that life may have originated around deep-sea hydrothermal vents, where superheated water rich in minerals spews from the Earth's crust. The extreme conditions found in these ecosystems provide a rich chemical environment conducive to the formation of complex organic molecules. This theory posits that these vent communities might have offered the necessary conditions for the first biological processes to occur, highlighting the potential for life to thrive in extreme environments. A third theory focuses on the idea of extraterrestrial origins, known as panspermia. This hypothesis suggests that microbial life, or at least the building blocks of life, could have been delivered to Earth via comets, meteoroids, or interstellar dust. The existence of robust organisms like tardigrades capable of surviving extreme conditions makes this theory plausible, as it raises the possibility that life or its precursors could survive the harsh journey through space. Lastly, some researchers explore the RNA world hypothesis, which posits that self-replicating ribonucleic acid molecules were the precursors to life. According to this theory, RNA could have served dual roles, acting as both genetic information, like deoxyribonucleic acid, and as a catalyst for biochemical reactions, much like proteins do today. This self-sufficient system would mark a pivotal stage in the transition from simple molecules to the complex cellular life forms we know today. These theories, while distinct, may not be mutually exclusive, and ongoing research continues to seek clarity on the remarkable journey from inanimate chemistry to the rich tapestry of life on Earth. Early Earth was a place of extreme and transformative environmental conditions, markedly different from the habitat we experience today. When the planet formed around 4.5 billion years ago, it was a hot and volatile landscape. The surface was characterized by intense volcanic activity, with magma oceans covering much of the globe. As the planet began to cool, the relentless bombardment from asteroids and comets contributed to a chaotic environment. This resulted in frequent impacts, which further shaped the developing surface while releasing gases trapped within the Earth. As temperatures gradually decreased, water vapor from volcanic eruptions began to condense, forming the first oceans. These ancient seas were likely acidic and rich in minerals, creating an environment conducive to complex chemistry. The composition of the atmosphere was vastly different at this time. It was primarily made up of carbon dioxide, nitrogen, water vapor, and various other gases like methane and ammonia. Notably, there was little to no free oxygen present, which meant that early life forms, if they existed, would have been anaerobic, thriving in environments without oxygen. Another significant factor was the surface temperature, which varied greatly due to greenhouse gases like carbon dioxide that trapped heat. These conditions created a warm and humid climate in some areas, while other regions experienced extreme temperatures. The presence of hydrothermal vents on the ocean floor introduced another dynamic aspect to the environment. These vents released heated, mineral-rich water that created unique habitats potentially rich in chemical energy, supporting the possibility of early life. In this extreme milieu, the interplay of geological and atmospheric changes continued to shape the planet. Over millions of years, Earth's environmental conditions became more stable, paving the way for the emergence of life. Understanding these early environmental conditions offers us valuable insights into how life could have originated and adapted, ultimately leading to the complex ecosystems we see today. The RNA world hypothesis is a compelling scientific theory that proposes ribonucleic acid, or RNA, was the first molecule to carry genetic information and catalyze biochemical reactions in the early stages of life on Earth. This idea suggests that life began with simple self-replicating RNA molecules, which later evolved into the more complex structures we observe today, such as deoxyribonucleic acid and proteins. This perspective fundamentally shifts our understanding of the origins of life, emphasizing the pivotal role RNA may have played in prebiotic chemistry. One of the key features of RNA that supports this hypothesis is its ability to serve as both a repository for genetic information and as a functional catalyst. Unlike deoxyribonucleic acid, which is primarily a stable storage medium for genetic instructions, RNA is capable of forming various three-dimensional shapes that allow it to catalyze chemical reactions. This dual role, acting as both an informant and a doer, makes RNA a prime candidate for the first self-replicating molecule, as it could facilitate the necessary reactions for replication while also encoding the information needed for future generations. Experimental research has demonstrated the plausibility of this hypothesis. Scientists have created RNA molecules in the laboratory that can replicate themselves and perform catalytic functions, supporting the idea that RNA-based life could theoretically emerge under the right conditions. These experiments highlight how RNA could have arisen from simpler prebiotic molecules through natural processes, eventually leading to the evolution of more complex life forms. The implications of the RNA world hypothesis extend beyond the origins of life. It raises intriguing questions about the nature of biological evolution itself. If RNA was indeed the precursor to DNA and proteins, understanding the early stages of life could provide insights into how life adapts and diversifies in response to environmental challenges. This hypothesis remains a crucial area of research, as scientists continue to explore the intricate pathways that may have led to the emergence of life on our planet. The formation of the first self-replicating molecules is a key focus in the study of the origins of life, and several theories attempt to explain how such complex structures could have come into being from simpler prebiotic compounds. One widely accepted framework suggests that these molecules arose through a series of chemical reactions in the primordial environment of early Earth. Researchers propose that simple organic molecules, possibly including amino acids and nucleotides, formed under specific conditions, such as those found near hydrothermal vents or in shallow warm pools. The key to self-replication lies in the ability of certain molecules to catalyze their own formation. It is believed that some nucleotides, the building blocks of ribonucleic acid, could spontaneously assemble into longer chains, creating primitive RNA-like molecules. Conditions such as evaporating ponds could concentrate these nucleotides, allowing them to polymerize through non-enzymatic processes. As these chains lengthened, they began to exhibit properties akin to those of self-replicating systems. This transition from simple building blocks to more complex structures may have been enhanced by the presence of minerals that acted as catalysts, facilitating the formation of longer nucleic acid strands. Thus, once these RNA-like molecules formed, they could have engaged in a rudimentary form of replication, where a single molecule might serve as a template for producing a complementary strand. Small errors in replication could have introduced variability, which is essential for evolution. Over time, some variants exhibiting more efficient self-replication would have had a higher likelihood of surviving and propagating, establishing a primordial fitness landscape that mirrors aspects of natural selection. This process may have been supported by the incorporation of alternative prebiotic molecules and varied environmental conditions. Researchers have suggested that the complex interplay of environmental factors, coupled with the inherent properties of nucleic acids, created a fertile ground for the emergence of early self-replicating systems. Although the precise details of this fascinating transition remain a subject of active research, the idea emphasizes a gradual, stepwise evolution from simple organic compounds to the intricate molecular machinery that characterizes life today. Hydrothermal vents are thought to have played a significant role in the origin of life on Earth, offering a unique environment that could facilitate the necessary chemical reactions for the emergence of living organisms. These underwater structures, found along mid-ocean ridges, release superheated, mineral-rich water from deep within the Earth's crust. The extreme conditions found at these vents, including high temperatures, pressure, and the presence of a variety of chemical compounds, create a dynamic ecosystem that may have been conducive to the formation of life. One of the critical aspects of hydrothermal vents is their potential to provide a rich source of energy. The geological activity surrounding these vents generates heat and utilizes chemical reactions, including the oxidation of minerals, which could serve as an energy source for early biochemical processes. This suggests that instead of relying solely on sunlight for energy, life's precursors may have developed in dark, nutrient-dense environments where chemical energy was available. In such environments, simple organic molecules might have formed from the various minerals present and could have been further transformed into more complex compounds. The structure of hydrothermal vents, particularly their chimneys, may also have played a role in concentrating the necessary chemicals and facilitating polymerization processes. These formations can create microenvironments that stabilize conditions, allowing for various reactions to occur more efficiently. As chemical reactions and interactions took place within these unique settings, the building blocks of life, such as amino acids and nucleotides, could have been synthesized and organized into more complex molecules. Moreover, the diverse communities of extremophiles, organisms that thrive in extreme conditions, found around these vents provide a glimpse into early biochemical processes. Some scientists speculate that life could have originated directly from these communities, which thrive on the chemical energy derived from vent fluids. This indicates that the conditions present at hydrothermal vents not only supported the synthesis of life's building blocks, but also created a habitat where primitive life forms could have survived and evolved. The ongoing research in this area continues to explore the fascinating possibilities of how these underwater environments contributed to the origins of life on our planet. Studying the origins of life in laboratories is a multidisciplinary endeavor that combines elements of chemistry, biology, geology, and planetary science. Scientists employ a variety of experimental techniques to simulate the conditions of the early Earth, aiming to recreate the processes that may have led to the emergence of life. One of the most well-known methods involves recreating the primordial environment in which organic molecules could form. Through simulations, researchers can mimic conditions such as high temperatures, volcanic activity, and the presence of various gases present in the early atmosphere. One commonly utilized approach is the synthesis of simple organic molecules from basic inorganic compounds. For instance, researchers conduct experiments similar to the famous Miller-Urey experiment, in which a mixture of gases believed to represent the early atmosphere is subjected to electric sparks to simulate lightning. This process has successfully produced amino acids, the building blocks of proteins, which suggests that life's fundamental components could form under prebiotic conditions. Such experiments help scientists understand how simple organic molecules could have assembled and evolved over time. Another vital area of research focuses on examining the self-assembly and replication of RNA molecules. Scientists perform experiments to explore how ribonucleic acid could form in conditions similar to those on the early Earth and whether it is capable of catalyzing its own replication. By studying various nucleotides, researchers are investigating how they might polymerize and replicate through non-enzymatic processes, providing insights into the RNA world hypothesis. These investigations also explore the selective pressures that could lead to the survival and propagation of certain RNA strands. Researchers also delve into the role of mineral surfaces, particularly those found near hydrothermal vents, which may facilitate critical chemical reactions. By exposing organic compounds to various minerals under simulated vent-like conditions, scientists can identify which environments foster the formation of complex molecules. This approach aims to uncover how life's building blocks could combine and evolve into self-replicating entities. Through these laboratory experiments, scientists gain valuable insights into the intricate steps that may have led to the origins of life, helping to crack one of the most profound mysteries in science. The earliest forms of life on Earth are believed to have been simple, single-celled organisms known as prokaryotes. These microorganisms appeared approximately 3.5 to 4 billion years ago, during a time when the planet was still relatively new and its conditions were harsh. The dominant types of prokaryotes are bacteria and archaea, which are characterized by their simple cellular structure without a nucleus or membrane-bound organelles. This simplicity allowed them to thrive in various environments, including extreme conditions that would be inhospitable to more complex life forms. Among the earliest forms of life were anaerobic organisms that did not require oxygen for survival. In fact, the atmosphere at the time contained very little free oxygen, making it necessary for these primitive life forms to rely on other metabolic processes for energy. Some of these early organisms utilized chemosynthesis, utilizing inorganic molecules like hydrogen sulfide or methane to produce energy. This ability allowed them to flourish in environments such as hydrothermal vents or deep sea areas, where sunlight could not penetrate. Evidence of these early life forms comes from ancient rock formations known as stromatolites, which are layered structures created by the activity of microbial mats, primarily composed of cyanobacteria. Cyanobacteria are photosynthetic organisms that played a crucial role in transforming the Earth's atmosphere by producing oxygen as a byproduct of photosynthesis. As these organisms proliferated, they contributed to the Great Oxygenation Event around 2.4 billion years ago, which dramatically increased atmospheric oxygen levels and laid the groundwork for the evolution of more complex life. Additionally, molecular studies of contemporary organisms suggest that common ancestors of all life share specific genetic traits, indicating a shared origin. This connection highlights how even the simplest forms of life have evolved over billions of years into the diverse array of organisms we see today. Understanding these early life forms provides crucial insights into the processes that shaped biological evolution and the adaptation of life on Earth. Photosynthesis developed as a crucial biological process around 2.7 billion years ago, primarily through the activity of early photosynthetic organisms such as cyanobacteria. These organisms possess the ability to convert light energy, typically from the sun, into chemical energy by using carbon dioxide and water as raw materials. The byproduct of this process is oxygen, which is released into the atmosphere. Initially, the Earth's atmosphere contained very little free oxygen, as it was dominated by gases such as carbon dioxide, methane, and ammonia. The emergence of photosynthesis marked a profound turning point in Earth's history, known as the Great Oxygenation Event. As cyanobacteria proliferated in the oceans, they began to release significant amounts of oxygen as a metabolic byproduct. Over millions of years, this accumulation of oxygen started to change the composition of the atmosphere. Prior to this event, the Earth's surface was largely anaerobic, and most living organisms thrived without oxygen. The introduction of free oxygen had dramatic effects, leading to the extinction of many anaerobic organisms that could not survive in this new oxidative environment. As atmospheric oxygen levels gradually rose, it facilitated the development of aerobic respiration, a more efficient method of energy production that uses oxygen. This shift opened up new ecological niches and allowed for the evolution of complex life forms. The buildup of oxygen also contributed to the formation of the ozone layer, which filtered harmful ultraviolet radiation from the sun, creating a more hospitable environment for terrestrial life. The impact of photosynthesis on Earth's atmosphere cannot be overstated. It instigated a fundamental change in the planet's biochemistry, paving the way for the diverse array of life forms that would eventually evolve. The oxygen produced by photosynthetic organisms laid the foundation for all aerobic life and set in motion a series of geological and climatic changes that continue to influence our planet today. Through the process of photosynthesis, life on Earth not only adapted to utilize the available resources, but fundamentally transformed the atmosphere and set the stage for future evolutionary advancements. The Great Oxygenation Event, often referred to as the oxygen crisis, occurred approximately 2.4 billion years ago and marks a pivotal moment in Earth's history. This event was characterized by a dramatic increase in atmospheric oxygen levels, primarily due to the photosynthetic activity of cyanobacteria, which began releasing oxygen as a byproduct of photosynthesis. Before this event, the Earth's atmosphere had very little free oxygen, making it a largely anaerobic environment where life thrived without this essential gas. The significance of the Great Oxygenation event cannot be overstated. As oxygen levels rose, they initiated profound changes not only in the atmosphere, but also in the biosphere and geosphere. One of the immediate consequences was the mass extinction of many anaerobic organisms that could not survive in an oxidative environment. The accumulation of oxygen led to the formation of reactive chemical compounds, further altering the conditions of life on Earth. This transition marked the end of a dominant era of anaerobic life and set the stage for the development of aerobic organisms that would eventually evolve. The influx of oxygen had a lasting effect on the planet's geology as well. Oxygen began to react with dissolved iron in the oceans, leading to the precipitation of iron oxides, which are still present today in banded iron formations. As the oxygen continued to accumulate, it contributed to the formation of the modern atmosphere, creating a protective ozone layer that shields the Earth from harmful ultraviolet radiation. This development made it possible for life to transition onto land and evolve into the diverse range of organisms that we see today. Overall, the Great Oxygenation event was significant because it catalyzed the evolution of complex life, fundamentally reshaped Earth's chemistry, and set a new trajectory for biological evolution. The changes initiated during this event have had a lasting impact, creating conditions that nurtured the rise of multicellular life forms and ultimately led to the complex ecosystems we find on Earth today. The evolution of multicellular life from single-celled organisms marks a critical transition in the history of life on Earth. This process likely began around 600 million years ago during the Ediacaran period, although the groundwork for multicellularity may have started much earlier. One key factor that facilitated this transition was the rise of simple colonial organisms, which formed clusters of cells that could function together while still maintaining their individual identities. Colonial living offered several advantages. Cells within a colony could cooperate and share resources, allowing them to better exploit their environment. Some cells could specialize in certain functions, such as nutrient acquisition or reproduction, which provided a competitive edge. Over time, these simple colonies likely evolved more intricate forms of communication and cooperation, leading to a more integrated and interdependent existence. This cooperation was essential as it allowed cells to work together more efficiently than they could individually, paving the way for the evolution of multicellular organisms that exhibited division of labor. Another crucial element in the transition to multicellularity was genetic regulation. As cells began to aggregate, variations in gene expression would allow for specialized functions to emerge within the same organism. This differentiation transformed these aggregates into more complex life forms where specific groups of cells took on designated roles, furthering the organism's overall efficiency and survivability. The ability to regulate genes and control development is a cornerstone of multicellular life and is seen in various lineages today. Environmental factors also influenced the evolution of multicellularity. Changes in the Earth's atmosphere and oceans, like increased oxygen levels, may have created new opportunities for larger organisms. The availability of ecological niches encouraged experiments in body plans and cellular organization, leading to the development of a wide variety of multicellular life forms, from simple algae and sponges to more complex plants and animals. This evolutionary trajectory has continued to unfold, resulting in the diverse ecosystems present today. The cooperation, specialization, and increasing complexity of cellular organization have allowed multicellular life to thrive and adapt in myriad ways throughout Earth's history. The emergence of complex life on Earth was driven by several major evolutionary innovations that fundamentally reshaped living organisms and their capacities. One of the earliest and most significant innovations was the development of multicellularity itself. This allowed cells to group together and specialize, leading to organisms with different cell types and functions. Specialization paved the way for more complex structures and systems, enabling organisms to perform various functions more efficiently than single-celled organisms could. Another critical innovation was the evolution of sexual reproduction. Unlike asexual reproduction, which involves a single organism replicating itself, sexual reproduction involves the combination of genetic material from two parents. This process increases genetic diversity within populations, enhancing adaptability and resilience. The introduction of genetic variation through sexual reproduction played a crucial role in the evolution of complex traits and the ability of organisms to respond to changing environments. The development of internal and external skeletons also marked a major advancement in complexity. For instance, the evolution of hard body structures allowed organisms to grow larger and provided protection against predation. Invertebrates, such as arthropods and mollusks, evolved exoskeletons, while vertebrates developed endoskeletons. These skeletal innovations not only supported increased body size and complexity, but also facilitated movement and the exploitation of new ecological niches. Further, the evolution of specialized tissues and organs was vital for the advancement of complex life forms. As multicellular organisms differentiated, specialized systems for digestion, circulation, and respiration emerged, supporting larger and more active organisms. For example, the development of the circulatory and respiratory systems in animals allowed for efficient nutrient and gas exchange, enabling higher metabolic rates and greater mobility. Lastly, the emergence of new ecological interactions, such as predation and symbiosis, fostered adaptive radiation and diversification. These interactions prompted evolutionary pressures that drove the development of complex traits, including improved sensory organs, defense mechanisms, and behavioral strategies. Each innovation built upon the previous ones, contributing to a web of complexity that ultimately led to the rich tapestry of life we observe today. Together, these evolutionary milestones laid the groundwork for the vast and diverse forms of complex life that inhabit our planet. Mass extinction events have played a critical role in shaping the course of evolution on Earth by dramatically altering ecosystems and creating opportunities for new life forms to emerge. Throughout the history of our planet, there have been 5 major mass extinctions, with each event resulting in the loss of a significant percentage of species across various taxa. These extinctions not only eliminated existing species, but also fundamentally reshaped ecological dynamics and opened new niches for surviving organisms. One of the most famous mass extinctions is the event at the end of the Cretaceous period, approximately 66 million years ago, which led to the demise of the dinosaurs. This event is believed to have been triggered by a combination of catastrophic factors, including an asteroid impact and volcanic activity. The extinction of dominant species like the dinosaurs allowed mammals, which had been small and relatively inconspicuous, to diversify and occupy the ecological spaces vacated by these larger reptiles. This adaptive radiation laid the groundwork for mammals to evolve into the varied forms we see today, including primates, marine mammals, and ultimately humans. Mass extinctions also have a profound impact on evolutionary trajectories. After each extinction event, the remaining species often undergo rapid diversification. This phenomenon, known as adaptive radiation, occurs when survivors exploit new environments or adapt to new conditions, leading to the development of novel adaptations and the emergence of entirely new groups of organisms. For example, after the Permian-Triassic extinction, which is considered the deadliest extinction event, many arthropods and early reptiles underwent extensive diversification, shaping the ecosystems of the subsequent Mesozoic era. Furthermore, mass extinctions can drive significant evolutionary changes by imposing selective pressure on remaining species. For instance, in the aftermath of a mass extinction, the traits that enable survival in the altered environment can be favored, leading to evolutionary innovations that may not have emerged otherwise. These changes can result in the evolution of new physical forms, reproductive strategies, and ecological interactions, thus further enhancing the diversity of life. Through these processes, mass extinction events have profoundly influenced the evolutionary narrative of life on Earth. Rather than merely slashing diversity, they have often catalyzed the emergence of new forms, adaptations, and evolutionary pathways, illustrating the dynamic nature of life in response to changing conditions. Each mass extinction has left its mark on the biosphere, fundamentally reshaping ecosystems and providing the context for the myriad forms of life that inhabit our planet today. The current understanding of human evolution is framed within the broader context of primate evolution and is supported by a wealth of fossil evidence, genetic data, and advances in anthropological research. Humans belong to the family Hominidae, which includes our closest living relatives, the great apes, chimpanzees, bonobos, gorillas, and orangutans. The evolutionary journey of humans traces back millions of years to the divergence of our lineage from the common ancestor we share with chimpanzees, which is estimated to have occurred around 5 to 7 million years ago. One of the earliest known hominins is Sahelanthropus chadensis, which lived about 6 to 7 million years ago. Fossils attributed to this species exhibit a mixture of features seen in both apes and later human ancestors, suggesting it was a critical early step in our evolutionary lineage. Over time, various species emerged, such as Australopithecus afarensis, represented by the famous fossil Lucy, which lived around 3 to 4 million years ago. These early hominins displayed both bipedalism, walking on 2 legs, and adaptations for climbing, indicating a lifestyle that involved both terrestrial and arboreal activities. As evolution progressed, the genus Homo emerged, characterized by larger brain sizes and more advanced tool use. Homo habilis, thought to have existed around 2 million years ago, is often regarded as one of the earliest members of our genus, showing evidence of using simple stone tools. This was followed by Homo erectus, who evolved roughly 1.9 million years ago and exhibited a combination of physical traits that indicate a more modern body structure, as well as the ability to control fire and create complex tools. Homo erectus spread out of Africa into other regions, marking one of the first hominin migrations. The evolution of modern humans, Homo sapiens, is believed to have occurred around 300,000 years ago in Africa. Genetic and fossil evidence suggests that as Homo sapiens evolved, they coexisted with other hominin species such as Neanderthals and Denisovans. Interbreeding events between these groups have left traces of their DNA in contemporary human populations. The migration of Homo sapiens out of Africa roughly 60,000 years ago led to the eventual colonization of the world and the development of diverse cultures and civilizations. Contemporary research continues to unveil the complex web of interactions and adaptations that shaped human evolution. This includes insights into the genetic, environmental, and social factors influencing our ancestors' development. The understanding of human evolution is an ongoing endeavor that integrates findings from multiple disciplines, revealing not only how we came to be as a species, but also our place within the broader story of life on Earth. Early hominins, our ancient ancestors, exhibited several notable differences from modern humans, primarily in physical structure and cognitive abilities. For instance, their skeletons were generally more robust and smaller, with a more pronounced brow ridge and a sloping forehead. Early species such as Australopithecus afarensis had long arms adapted for climbing, indicating their lifestyle included significant time spent in trees, unlike modern humans, who are primarily terrestrial. In terms of brain size, early hominins had smaller cranial capacities compared to our average modern brain. This difference influenced their cognitive functions. While early hominins likely displayed some problem-solving skills and basic tool use, they lacked the advanced language and complex social structures that characterize modern human societies. The development of sophisticated communication and abstract thinking is a defining feature that distinguishes us from our early relatives. The environmental adaptations of these hominins also shaped their differences. Many early hominins lived in diverse habitats ranging from open savannas to dense forests. Their dietary requirements would have varied considerably, often relying on scavenging and foraging rather than the organized agriculture that defines human civilization today. Such dietary approaches significantly influenced their physical development and behaviors. Another key distinction is in cultural evolution. Early hominins exhibited rudimentary tool-making techniques using simple stones and sticks, while modern humans have developed a vast array of technologies, from simple implements to sophisticated machinery. The process of passing down knowledge and skills across generations has allowed modern humans to create intricate societies and reshape environments in unprecedented ways, setting us apart from our ancestors. This ongoing evolution of culture and technology continues to define what it means to be human. Climate change has been a significant force in shaping human evolution, influencing not only the physical characteristics of early hominins, but also their behavior and societal structures. Over millions of years, Earth has experienced cycles of cooling and warming, affecting the habitats available to our ancestors. During times of climate fluctuation, environments would shift from forests to savannas and back, compelling early hominins to adapt to diverse conditions or migrate to survive. These adaptations paved the way for the development of key traits in our lineage. As the climate changed, particularly during periods of significant glaciation and subsequent warming, early hominins were forced to exploit new resources. This included shifting their diets from primarily foraged fruits and leaves to include more varied sources like meat. The ability to adapt to a hunting and gathering lifestyle may have contributed to the development of larger brains, as the increase in protein and energy intake supported more complex cognitive functions. This shift played a crucial role in sparking the evolutionary advantages that would eventually lead to the emergence of Homo sapiens. Moreover, the environmental challenges posed by climate change necessitated enhanced social cooperation and communication among groups. As food sources became more sporadic, early humans began to rely on one another for survival, fostering social bonds and developing early forms of language. This ability to communicate and work together not only improved their chances of survival, but also laid the groundwork for the complex societies that would follow, enabling the exchange of ideas and technologies. Lastly, understanding climate change has shaped the migration patterns of early humans. As habitats transformed, groups dispersed across continents in search of suitable living conditions. This migration led to encounters with diverse environments and climates, influencing genetic diversity and adaptation. Ultimately, the interplay between changing climates and human adaptability has been a driving force in our evolutionary history, illustrating how closely intertwined our species has been with the planet's ecological changes. The development and use of tools marked a pivotal moment in human evolution, significantly impacting both physical and cognitive development. Early hominins, such as Homo habilis, began crafting simple stone tools around 2 million years ago, which greatly enhanced their ability to hunt, gather, and process food. These early tools allowed our ancestors to obtain a wider range of resources, contributing to a more nutrient-rich diet that supported larger brains. Over time, the improvement and diversification of tools led to the capability for more complex tasks, facilitating advancements in technology and culture. The control of fire introduced a transformative element in human development. Mastering fire offered multiple advantages. First, it provided heat and light, allowing early humans to extend their activities into the night and survive colder climates. More critically, the ability to cook food revolutionized their diet. Cooking not only made food easier to digest, but also enhanced nutrient absorption, making more energy available. This dietary shift likely played a crucial role in supporting the growth of larger brains and the development of social structures, as sharing cooked meals could have fostered community bonding. Tool use and fire also encouraged the evolution of complex social behaviors. As early humans collaborated in hunting or cooking, they began to develop social networks that facilitated communication and cooperation. This reliance on teamwork would eventually lead to the formation of more intricate societies as groups shared knowledge, skills, and resources. The exchange of ideas and innovations struggled against the backdrop of environmental challenges, proving essential for survival and further development. Moreover, the advancements in tool-making and the use of fire reflected an increasing proficiency in problem-solving and abstract thinking. As these skills flourished, they led to innovations not solely in material culture, but also in the way early humans perceived and interacted with their environment. This newfound ingenuity laid the foundation for the diverse technologies and complex cultural practices that define modern human life, showcasing how fundamental these developments were in shaping our species. Genetic evidence has profoundly enriched our understanding of human evolution, providing insights that enhance and sometimes refine our interpretations of the fossil record. The comparison of DNA across different species, particularly ancient and modern humans, reveals a complex web of ancestry and migration. One of the most compelling pieces of evidence comes from the study of mitochondrial DNA, inherited exclusively from mothers. This genetic material has allowed scientists to trace maternal lineages back thousands of generations, giving rise to the concept of a mitochondrial Eve. This hypothetical common ancestor lived in Africa approximately 100,000 to 150,000 years ago, highlighting the African roots of all modern humans. Additionally, the analysis of nuclear DNA has provided vital information. By sequencing genomes from ancient human remains, researchers can discern genetic variations that have emerged over time. Notable discoveries, such as the Neanderthal Genome Project, indicate that modern non-African humans carry approximately 1 to 2% Neanderthal DNA, suggesting that at some point our ancestors interbred with Neanderthals. This intermingling may have conferred certain adaptive traits, potentially influencing skin color and immune responses among populations. Beyond Neanderthals, the study of ancient DNA has also shed light on other archaic hominins. For example, genetic material extracted from Denisovans, a distinct group of ancient humans, has uncovered more layers in our evolutionary history. Some modern human populations, particularly those in Southeast Asia and Oceania, carry Denisovan DNA, indicating that these early humans also contributed to the genetic diversity of contemporary humans. Such findings emphasize that human evolution is not a linear process, but a complex interplay involving multiple hominin species. Finally, the growth of genomic technologies has allowed for increasingly sophisticated analyses of genetic data, revealing how adaptations to environmental changes have occurred over time. For instance, genes linked to traits such as lactose tolerance, skin pigmentation, and even altitude adaptation have been studied in depth. These genetic adaptations illustrate how different human populations responded to varying ecological pressures, further enhancing our understanding of the dynamic relationship between genetics and evolution. Together, these strands of genetic evidence weave a comprehensive picture of our evolutionary past, highlighting the diversity of experiences and adaptations that have shaped the human story. Human migration patterns have played a crucial role in shaping the diversity of our species, influencing genetic makeup, cultural practices, and social structures. As early humans began to leave their African origins and spread into other parts of the world, they encountered different environments, climates, and challenges. This dispersal triggered adaptations to local conditions, leading to variations in physical traits such as skin color, body shape, and even physiological responses to diseases. One of the most significant factors in shaping diversity was the adaptation to geographical barriers and environmental contexts. For instance, populations that migrated into colder regions developed traits such as lighter skin, which enhances vitamin D synthesis under low sunlight. Conversely, those who remained in equatorial regions retained darker pigmentation, offering protection against UV radiation. These adaptations demonstrate how environmental pressures directly influence the evolutionary trajectory of human populations, resulting in a rich tapestry of genetic diversity. Cultural practices also evolved in tandem with migration. As groups settled in new areas, they developed unique ways of life, including language, dietary preferences, and social structures. The exchange of ideas and technologies among migrating groups fostered innovation and cultural enrichment. For example, the spread of agriculture transformed societies, altering not only human diets but also the structures of communities, leading to the establishment of cities and trade networks. This cultural diversity has significantly contributed to the richness of human experience throughout history. Moreover, the patterns of migration often led to interbreeding among different populations, further diversifying our genetic heritage. As humans migrated and settled in new regions, they came into contact with other groups, facilitating gene flow that introduced new genetic variations. This exchange has implications for health, as certain genetic traits can result in advantages or susceptibility to particular diseases based on environmental factors or lifestyle changes. Overall, human migration facilitated a continuous interplay of adaptation, cultural evolution, and genetic variation that has shaped our species. The legacy of these movements can still be seen today, as modern populations bear the genetic imprint of their ancestors' journeys and experiences. The diversity we observe now is a testament to the resilience and adaptability that have characterized humanity throughout its history. The development of agriculture was a transformative shift in human history, profoundly impacting societies and lifestyles across the globe. One of the primary factors that contributed to this transition was the end of the last ice age, around 10,000 to 12,000 years ago. This climatic shift resulted in warmer temperatures, favorable conditions for the growth of wild grains, and a gradual transformation of ecosystems. As ecosystems changed, certain plants and animals became more abundant and accessible, encouraging early hunter-gatherers to begin experimenting with cultivation and domestication. Population growth also played a critical role in the rise of agriculture. As human groups began to settle in favorable areas with abundant resources such as river valleys, they experienced less seasonal mobility and established more permanent settlements. This increase in population created higher demand for food resources, prompting communities to explore farming as a means to supplement their diets. A reliable food source allowed for greater population density, leading to the complexities of social organization and community life that are characteristic of agricultural societies. The development of social structures and technological advancements further facilitated agricultural practices. As communities grew, individuals began to specialize in various tasks, moving beyond merely foraging for food. This specialization led to innovations in tools and techniques for planting and harvesting. Advances in pottery and irrigation also allowed for better storage and management of surplus food, enabling communities to sustain larger populations and survive in times of hardship. With a more stable food supply, these advancements supported the rise of permanent settlements and ultimately the development of civilizations. Additionally, cultural factors influenced the shift toward agriculture. Humans have a natural tendency to influence their environment, and as they began to cultivate and breed plants and animals, they fostered a deeper connection to these resources. The desire for control over food sources not only reduced vulnerability to environmental fluctuations, but also became intertwined with spiritual and social practices. The incentives to cultivate familiar staple crops and domesticate animals were driven not just by necessity, but also by the cultural value placed on these activities. The development of agriculture arose from a complex interplay of environmental changes, population pressures, technological advancements, and cultural factors. Each of these elements contributed to the establishment of farming practices that would reshape human societies, leading to the rise of civilizations and the intricate social systems we see today. The formation of early civilizations around river valleys can be attributed to several interconnected factors. First and foremost, river valleys provided access to fertile land, ideal for agriculture. The nutrient-rich silt deposited by annual flooding created superb conditions for growing crops, making these areas highly conducive to farming. This agricultural bounty allowed communities to both cultivate surplus food and sustain larger populations, laying the groundwork for the development of complex societies. In addition to fertile soil, rivers served as a vital water source. Early agricultural societies depended on rivers for irrigation, which enabled them to expand their farming activities beyond naturally wet areas. By devising methods to control and direct water flow, these civilizations could ensure consistent crop yields, supporting the growth of communities. This not only improved food security, but also encouraged people to settle in one location rather than perpetually migrate in search of resources. Trade and transportation were also significant advantages offered by river valleys. Rivers provided natural highways that facilitated the movement of goods, people, and ideas between emerging communities. This connectivity promoted trade and economic exchange, which further spurred population growth and cultural development. As groups interacted through trade, they shared technologies, agricultural practices, and cultural beliefs, enriching their societies and fostering a more complex social framework. Finally, the abundance of resources and population density created opportunities for specialization. As agricultural production increased, individuals began to focus on various crafts and trades, moving beyond subsistence farming. This specialization led to the emergence of diverse professions, from artisans to religious leaders, and the establishment of social hierarchies. The concentration of people in river valley settlements also facilitated the development of governance structures as communities organized themselves to manage resources and uphold order, paving the way for organized political systems and elaborate cultural practices. Overall, the unique combination of fertile soil, reliable water sources, trade routes, and the ability to support larger populations made river valleys hub centers for early civilizations. As these communities flourished, they set the stage for the rise of complex societies that would shape human history in profound ways. The development of cities was driven by several key innovations that transformed human societies and laid the groundwork for urban life. One of the most significant innovations was advancements in agriculture. The introduction of new farming techniques, such as crop rotation and irrigation methods, allowed for increased agricultural productivity. With more reliable food sources, communities could support larger populations, leading to greater density in settlements. This agricultural surplus freed some individuals from the demands of subsistence farming, creating opportunities for specialization in various trades and professions. Another crucial innovation was the development of infrastructure. Once settled populations grew, there was a need for organized systems to facilitate transportation and commerce. The construction of roads, bridges, and canals allowed for efficient movement of goods and people, fostering trade and connectivity between burgeoning cities. These transport networks not only supported local economies, but also encouraged cultural exchange and the sharing of ideas, contributing to the overall growth of urban environments. Social and political organization also evolved significantly during this period. The need for governance in increasingly complex societies led to the establishment of leadership structures and legal systems. Innovative forms of administration arose, enabling cities to manage resources, resolve conflicts, and maintain order. This was often accompanied by the emergence of bureaucracies that facilitated record-keeping, taxation, and public works projects, laying the foundation for the intricate political systems characteristic of urban life. Finally, advancements in technology contributed to the development and sustainability of cities. Innovations in building materials such as fired brick allowed for the construction of more durable structures which could accommodate the growing population and specialization. Moreover, inventions like pottery and metallurgy played important roles in everyday life and trade, enhancing both domestic routines and economic activities. Together, these innovations created the conditions necessary for cities to flourish, leading to the diverse urban landscapes we recognize today. Writing systems evolved as a means to record information, communicate ideas, and preserve culture, significantly impacting human societies. The earliest forms of writing emerged around 5,000 to 6,000 years ago, when civilizations began transitioning from oral traditions to written records. Initially, people used simple pictographs and symbols to represent objects or concepts, largely for practical purposes such as tracking resources, managing trade, and recording agricultural yields. Mesopotamia's cuneiform and Egypt's hieroglyphs are among the earliest examples, reflecting the needs of complex societies to keep systematic accounts of transactions and events. As societies grew in complexity, so did their writing systems. The evolution from simple pictures to more abstract symbols allowed for increased versatility in communication. Syllabic and alphabetic writing emerged, making it easier to represent spoken language and expand the range of ideas that could be expressed. This development democratized access to literacy and education, enabling a greater number of individuals to learn and engage with written content. As a result, the transmission of knowledge and cultural practices across generations became more reliable, transforming how societies viewed history, mythology, and lore. The impact of writing on human societies was profound and far-reaching. It fostered the establishment of centralized governments by enabling record-keeping on a scale previously unattainable. Legal codes, administrative documents, and treaties could be drafted and preserved, ensuring continuity and order within communities. Written language also facilitated the growth of complex bureaucracies, allowing for efficient management of resources, trade, and labor forces. Beyond administration, writing sparked cultural and intellectual development. It led to the creation of literature, philosophy, and scientific inquiry, fostering a shared identity among communities and enabling the exploration of abstract concepts. The preservation of knowledge through written texts allowed subsequent generations to build upon previous discoveries, leading to advancements in various fields of study. Ultimately, writing systems played a crucial role in shaping human civilization, enhancing communication, preserving cultural heritage, and laying the groundwork for modern societies. Trade has historically been a powerful catalyst in the spread of ideas and technologies, acting as a conduit for cultural exchange and innovation. As civilizations began to engage in commerce, caravans, ships, and trade routes connected distant regions, facilitating interaction among disparate cultures. This interaction allowed traders not only to exchange goods, but also to share knowledge, practices, and technologies. For example, the Silk Road, connecting Asia to Europe, became a vital network for the movement of products like silk, spices, and precious metals, as well as ideas such as religious beliefs, artistic expressions, and scientific knowledge. One striking example of this exchange is the spread of agricultural practices and technologies. As traders moved between regions, they brought crops and farming techniques that had developed in their homelands. The introduction of new agricultural products, such as rice from Asia to Africa and Europe, or maize and potatoes from the Americas to the rest of the world, allowed societies to diversify their diets and improve food security. These innovations not only boosted agricultural productivity, but also transformed social structures and spurred population growth. Moreover, trade facilitated the diffusion of technologies that enhanced production and quality of life. Innovations in metallurgy, textile production, and building techniques often moved along trade routes as skilled artisans shared their knowledge. This exchange of technology was particularly evident during the rise of empires, where the demand for luxury goods led to the adoption of advanced techniques from conquered and neighboring cultures. For instance, the spread of papermaking technology from China to the Islamic world and subsequently to Europe had profound effects on education, administration, and communication. In addition to goods and technologies, trade fostered the exchange of philosophical, religious, and artistic ideas, enriching cultural landscapes. Interactions among traders and merchants led to the blending of beliefs, resulting in the spread of religions such as Buddhism, Islam, and Christianity along trade routes, influencing societies across vast distances. Artistic styles and practices were also shared, leading to the flourishing of unique hybrid cultures in regions where trade flourished. Through these myriad channels, trade has played a critical role in shaping human history, intertwining societies and driving collective progress. The consequences of these interactions continue to resonate in our modern world, reflecting the enduring legacy of trade as a conduit for the flow of knowledge, technology, and culture. Energy revolutions, such as the advent of steam power and electricity, have dramatically shaped human progress by transforming economies, societies, and daily life. The Industrial Revolution in the late 18th and early 19th centuries marked a significant turning point with the widespread adoption of steam engines. This innovation enabled efficient mechanization of industries such as textiles and manufacturing, leading to mass production and a significant increase in productivity. Factories could now produce goods at an unprecedented scale, fueling economic growth and creating new job opportunities while also drawing populations into urban areas. Moreover, the steam revolution revolutionized transportation. The development of steam-powered locomotives and ships drastically reduced travel time and costs, reshaping trade networks and domestic markets. This enhanced mobility facilitated not only the movement of goods, but also the exchange of ideas and cultures across regions. The interconnectedness that arose from improved transportation networks laid the groundwork for globalization, paving the way for expanded markets and international trade. The advent of electricity in the late 19th and early 20th centuries further propelled human progress by enabling innovations that drastically changed everyday life. With the ability to harness electrical energy, cities grew increasingly vibrant as electric lighting illuminated streets, extended work hours, and transformed living conditions. Additionally, the rise of electrical appliances revolutionized household tasks, improving quality of life and freeing individuals, particularly women, from labor-intensive chores. 2. Electricity also catalyzed subsequent technological advances. It facilitated the development of communication technologies, such as the telephone and radio, which ultimately transformed how people interacted and shared information. The invention of computers in the mid-20th century, powered by electric energy, epitomized this trend, ushering in the digital revolution and reshaping societies in ways previously unimaginable. The ability to process information rapidly and connect people globally has had profound implications for education, commerce, governance, and interpersonal relationships. Together, these energy revolutions have driven unprecedented social and economic transformations. They have allowed for the growth of large-scale industries, urbanization, improved living standards, and interconnected global networks. The continual evolution of energy systems continues to shape human progress, challenging societies to adapt to new technologies while addressing the urgent issues of sustainability and environmental responsibility in a world increasingly reliant on energy. Our understanding of the atom has undergone significant evolution since the ancient Greeks proposed early ideas about the nature of matter. In the 5th century BCE, philosophers like Democritus suggested that all matter is composed of tiny, indivisible particles called atoms. While these ideas were largely philosophical and lacked empirical evidence at the time, they laid the groundwork for future inquiries into the nature of matter. The modern scientific understanding of the atom began to take shape in the early 19th century with the work of John Dalton. Dalton proposed that atoms were the fundamental building blocks of matter, each element consisting of unique atoms that combined in fixed ratios to form compounds. His atomic theory, which also suggested that atoms cannot be created or destroyed during chemical reactions, provided a systematic framework for understanding chemical interactions and marked a significant leap in atomic theory. The discovery of the electron at the turn of the 20th century by J.J. Thomson further advanced our understanding. Thomson's experiments with cathode rays revealed that atoms were not indivisible, as he identified particles smaller than the atom itself. This discovery led to the plum pudding model of the atom, where negative electrons were thought to be embedded in a positively charged soup. However, this model was soon challenged by Ernest Rutherford's gold foil experiment in 1912, which demonstrated that atoms have a dense, positively charged nucleus surrounded by electrons, leading to the nuclear model of the atom. As research progressed, the development of quantum mechanics in the early 20th century transformed our perception of atomic structure. Niels Bohr introduced his model, suggesting that electrons occupy specific energy levels or shells around the nucleus, but even this model was later refined. Quantum mechanics revealed the probabilistic nature of electron positions, leading to the current understanding of atomic orbitals. The atom is now viewed as a complex system governed by quantum principles, where electrons exist in probabilistic clouds rather than fixed paths. This ongoing evolution of atomic theory has profound implications for science and technology. It has informed the development of fields such as chemistry, physics, and materials science, leading to innovations in nuclear energy, medicine, and electronics. Our understanding of the atom continues to evolve, driven by advancements in experimental techniques and theoretical models, as scientists explore deeper realms of subatomic particles and interactions, revealing the fundamental nature of matter and the universe. The development of the scientific method was a gradual process influenced by various historical, philosophical, and cultural factors, particularly during the Renaissance and the scientific revolution. One of the key elements was the growing emphasis on empirical observation and rational thought, stemming from a revival of interest in ancient Greek and Roman texts. Scholars like Aristotle had previously laid the groundwork for systematic inquiry. But it was during the Renaissance that thinkers began to challenge traditional authorities, fostering a spirit of inquiry and skepticism that would shape the scientific method. In the 16th and 17th centuries, figures such as Nicholas Copernicus, Galileo Galilei, and Johannes Kepler further advanced empirical approaches to understanding the natural world. Copernicus's heliocentric model of the solar system, which posited that the Earth revolves around the Sun, challenged the long-held geocentric view. Galileo's use of controlled experiments and systematic observations with the telescope laid the foundation for modern experimental science. His advocacy for observation as a critical component of scientific inquiry exemplified a departure from reliance solely on philosophical reasoning or medieval scholasticism. The formulation of the scientific method can be attributed to key thinkers such as Francis Bacon and René Descartes. Bacon emphasized the importance of inductive reasoning, deriving general principles from specific observations as a systematic approach to understanding nature. He encouraged scientists to collect data through experiments and gather empirical evidence. Meanwhile, Descartes stressed the importance of deductive reasoning, advocating for a rational, methodical approach to problem-solving that relies on mathematical principles. Both philosophers contributed to a framework that combined induction, deduction, and careful experimentation. The scientific method was further refined through the works of later scientists, such as Isaac Newton, whose Principia Mathematica unified previous theories through mathematical principles and rigorous testing. The scientific community began to adopt a standardized approach to inquiry, which included the formulation of hypotheses, systematic experimentation, observation, and the use of evidence to draw conclusions. This framework not only provided a mechanism for testing ideas, but also encouraged collaboration and peer review, significantly advancing scientific knowledge. The development of the scientific method emerged from a rich interplay of historical and intellectual factors, challenging established authorities and emphasizing observation and experimentation. It represents a significant shift in how humanity seeks to understand the natural world, leading to remarkable advancements in science and technology that continue to influence modern civilization. Space exploration has significantly expanded our understanding of the universe, providing insights that were once beyond our reach. Beginning in the mid-20th century, the launch of artificial satellites and crewed missions marked the dawn of an era that would fundamentally alter our perspective on space and our place within it. The ability to send spacecraft beyond Earth's atmosphere allowed scientists to observe celestial phenomena with unprecedented clarity, leading to groundbreaking discoveries about our solar system and beyond. One of the most notable achievements was the Apollo missions, which culminated in human landings on the Moon. This monumental event not only showcased human ingenuity, but also provided direct samples of lunar rock and soil, enhancing our understanding of the Moon's geological history. The Apollo missions prompted further curiosity about planetary formation and the conditions necessary for life, igniting scientific inquiries that continue to this day. The examination of these samples revealed insights into the early solar system's formation and the processes that shaped terrestrial bodies. Following the success of lunar missions, the deployment of robotic spacecraft enabled the exploration of the outer planets and their moons. Missions such as Voyager, Galileo, and Cassini expanded our knowledge of the gas giants, their rings, and their numerous moons. Insights gained from these missions reshaped our understanding of planetary atmospheres, magnetic fields, and potential habitability. For example, the discovery of water vapor on Europa and geysers on Enceladus suggests that these icy moons may harbor conditions suitable for life, prompting further investigation into the possibilities of extraterrestrial life within our solar system. Moreover, advancements in telescopes and observational technology have revolutionized our understanding of the broader universe. Powerful ground-based telescopes and space observatories like the Hubble Space Telescope have opened new windows into deep space, allowing scientists to observe distant galaxies, nebulae, and cosmic phenomena. The detection of exoplanets, many of which exist in habitable zones, has expanded our search for life beyond Earth, informing theories on planetary systems and the potential for life in diverse environments. Overall, space exploration has dramatically enhanced our comprehension of fundamental questions about the universe. It has illuminated our understanding of celestial mechanics, the origins of cosmic structures, and the nature of time and space itself. Each mission contributes layers of information that reshape scientific paradigms, motivating future exploration and fostering a deeper appreciation for the vast, dynamic universe we inhabit. Studying the early universe requires a range of advanced technologies that enable scientists to gather and analyze data from distant cosmic phenomena. One of the fundamental technologies is the telescope, particularly space telescopes that operate outside Earth's atmosphere. Instruments like the Hubble Space Telescope have revolutionized our ability to observe astronomical objects by providing high-resolution images and spectra of distant galaxies and cosmic events. Hubble's ability to observe in various wavelengths, from ultraviolet to infrared, allows astronomers to study the light from early galaxies, shedding light on their formation and evolution. Another crucial technology is radio astronomy, which allows scientists to detect and analyze cosmic microwave background radiation. This remnant radiation from the Big Bang offers invaluable insights into the universe's earliest moments, revealing information about its composition, temperature fluctuations, and the acceleration of cosmic expansion. Observatories such as the Atacama Large Millimeter Submillimeter Array have advanced our understanding of this radiation, helping to paint a clearer picture of the universe's infancy. Spectroscopy is a vital technique that plays a significant role in studying the early universe. By dispersing light from distant celestial objects into its component colors, astronomers can identify the chemical composition, temperature, and motion of those objects. This technique has proven instrumental in discovering the processes that led to the formation of stars, galaxies, and even the conditions present during the universe's infancy. The study of the light spectrum enables scientists to trace the evolution of elements from the early universe to the present day. Lastly, advancements in computational technology and simulations have transformed our understanding of cosmic evolution. High-performance computing allows scientists to run detailed simulations of cosmic events, such as galaxy formation and the behavior of dark matter. These models, combined with observational data, help to test theories regarding the early universe and provide predictions that can be compared against real astronomical observations. Together, these key technologies shape our ability to study the early universe, enabling us to delve into its origins and the fundamental processes that have shaped the cosmos we observe today. Each technological advancement contributes layers of understanding, constantly refining our knowledge of how the universe began and evolved over billions of years. Computer technology has revolutionized the way we model cosmic processes, ushering in an era of unprecedented insight into the universe. Advanced computing power allows scientists to simulate complex phenomena that were once too intricate to understand. For instance, processes such as galaxy formation, stellar evolution, and cosmic microwave background radiation can now be modeled with remarkable precision. These simulations help researchers visualize cosmic events from the birth of stars to the collision of galaxies, transforming abstract theories into dynamic visual representations. High-performance computing environments, often utilizing thousands of processors working in tandem, dramatically speed up simulations. This capability allows for the modeling of vast scales of space and time that would take human researchers an impractical length of time to work through manually. The creation of three-dimensional simulations helps to study the intricate gravitational interactions occurring over millions of light-years, revealing patterns and structures that are vital to our understanding of the universe's history and composition. Artificial intelligence plays a crucial role in the evolution of cosmic modeling. Machine learning algorithms can analyze vast datasets generated by these simulations and even observed phenomena, identifying patterns and making predictions that humans might overlook. This melding of AI with astrophysics opens new pathways for discovery, enabling scientists to tackle previously intractable problems related to dark matter, dark energy, and the formation of cosmic structures. Moreover, computer technology has bridged the gap between theoretical astrophysics and observational data. With the rise of big data techniques, researchers can now integrate observational findings with simulations, leading to a more comprehensive understanding of cosmic events. As technology continues to evolve, so too will our capacity to explore and unravel the mysteries of the cosmos. Artificial intelligence is becoming a transformative force in modern cosmology, enhancing the way researchers analyze data and test theories about the universe. One of the most significant roles AI plays is in processing the vast amounts of observational data generated by telescopes and spacecraft. With the advent of powerful telescopes that capture images of billions of galaxies, the sheer volume of data can be overwhelming. Machine learning algorithms can intelligently sift through this information, identifying patterns and anomalies much faster than any human could. In addition to data analysis, artificial intelligence aids in the simulation of cosmic phenomena. Sophisticated algorithms can create detailed models of complex processes such as star formation and galaxy collisions, allowing scientists to predict outcomes based on varying conditions. These simulations enable researchers to understand not just current models, but also the evolution of the universe across billions of years. AI helps refine these models by continually updating them with new data and insights, making them more accurate and reliable. Moreover, machine learning techniques are used to automate and enhance the process of classifying astronomical objects. For example, AI can distinguish between different types of supernovae or identify exoplanets in star systems with incredible speed and accuracy. This capability not only accelerates discoveries, but also allows scientists to focus on interpreting results rather than on the tedious task of sorting through data. Artificial intelligence is also paving the way for new theories in cosmology. By employing unsupervised learning methods, researchers can unearth unexpected relationships within complex datasets, potentially leading to the discovery of new physical principles or phenomena. As computer technology continues to advance and the datasets grow even larger, the synergy between artificial intelligence and cosmology will likely unlock further mysteries of the cosmos that remain hidden today. The observable universe is a fascinating tapestry woven from various components, primarily dominated by dark energy, dark matter, and ordinary matter. Dark energy, which makes up about 70% of the universe, is a mysterious force that is believed to drive the accelerated expansion of the cosmos. Its exact nature remains one of the biggest puzzles in cosmology, profoundly influencing the structure and fate of the universe. Following dark energy, dark matter constitutes roughly 25% of the universe's composition. Although it does not emit, absorb, or reflect light, dark matter exerts gravitational forces that affect the motion of galaxies and galaxy clusters. This unseen mass helps glue galaxies together, and its presence is inferred from gravitational effects on visible matter. While research continues to identify the particles that make up dark matter, its influence is undeniable in shaping cosmic structures. Ordinary or baryonic matter accounts for just about 5% of the total composition. This form of matter includes everything we can observe, from stars and planets to gas and dust. The matter that forms galaxies, celestial bodies, and even life itself is a minor player in the grand scheme of the universe's total mass-energy content. Baryonic matter is distributed unevenly across the cosmos, creating the rich variety of structures we see today. Research into the composition of the universe is ongoing, expanding our understanding of these components and their interactions. Observations from advanced telescopes and experiments designed to detect dark matter and dark energy are constantly refining our knowledge. As scientists continue to delve into these intriguing aspects, they are effectively piecing together the cosmic puzzle that reveals the nature of our universe. The expansion of the universe is currently measured through a phenomenon known as the Hubble constant, which describes how fast galaxies are moving away from each other as a function of their distance. This rate of expansion is estimated to be about 70 kilometers per second for every 3.2 million light-years of distance. This means that distant galaxies are receding from us, and the farther away they are, the faster they appear to be moving. What this rapid expansion reveals is that the universe has been growing since its inception in the Big Bang, which occurred approximately 13.8 billion years ago. The current rate of expansion suggests that the universe is not only expanding, but that the rate of this expansion is accelerating. This acceleration is attributed to dark energy, a mysterious force that counteracts gravity and pushes galaxies apart. The discovery of this accelerating expansion has reshaped our understanding of cosmology and hints at the existence of forces and components that we have yet to fully comprehend. The implications of an expanding universe extend beyond mere numbers. It raises profound questions about the ultimate fate of the cosmos. If the rate of expansion continues to increase, one possibility is that galaxies could eventually drift so far apart that the observable universe will become an isolated collection of stars and galaxies, potentially ending in what is known as the Big Freeze. However, should the universe's expansion slow, it might lead to different scenarios, such as eventual gravitational collapse. Understanding the expansion rate not only informs us about the universe's past, but also serves as a window into its future. As researchers aim to refine the measurements of the Hubble constant and enhance our grasp of dark energy, we edge closer to unlocking the fundamental principles governing the cosmos. Each revelation brings us closer to unraveling the mysteries of existence itself. The cosmic microwave background is a faint glow of radiation that permeates the entire universe, and it is one of the most significant pieces of evidence supporting the Big Bang theory. This background radiation is essentially the afterglow of the hot, dense state of the universe that existed shortly after its formation, specifically about 380,000 years after the Big Bang. At this stage, the universe had expanded and cooled enough for protons and electrons to combine and form neutral hydrogen atoms, allowing light to travel freely for the first time. As the universe continues to expand, this primordial light has redshifted, shifting from the visible spectrum into the microwave range. Today it can be detected as a uniform background radiation, with a temperature of about 2.7 degrees above absolute zero. This remarkable consistency across the sky provides a wealth of information about the early universe, revealing crucial details about its origins, composition, and evolution. Scientists analyze the minute fluctuations in temperature and density found within the cosmic microwave background. These tiny variations represent the primordial density fluctuations from which galaxies and large-scale structures eventually formed. By studying these anomalies, researchers can glean insights into the composition of the early universe, including the relative amounts of ordinary matter, and dark energy. This analysis also allows scientists to estimate important cosmological parameters, such as the universe's age and its rate of expansion. The cosmic microwave background serves as a remarkable cosmic fossil, giving us a snapshot of the universe at a formative stage. As telescopes and instruments improve, we gain even more precision in observing these ancient remnants. Each new discovery not only deepens our understanding of the universe's early conditions, but also aids in testing and refining current cosmological models, allowing us to piece together the grand story of cosmic evolution. Galaxy clusters are vast groupings of galaxies bound together by gravity, often housing hundreds or even thousands of individual galaxies. These clusters are the largest gravitationally bound structures in the universe and typically span millions of light-years across. They often contain additional components, such as dark matter, hot gas, and even supermassive black holes at their centers. Understanding galaxy clusters is crucial because they serve as laboratories for studying the fundamental forces and processes that shape the cosmos. Galaxy clusters form through a process known as hierarchical clustering, where smaller groups of galaxies gradually merge to create larger structures over cosmic time. Initially, tiny density fluctuations in the early universe, driven by gravitational instabilities, prompted the accumulation of matter. These fluctuations attracted gas and dark matter, forming protoclusters. As time progressed, these protoclusters gathered additional matter and merged with other groups, leading to the formation of the massive clusters we observe today. Within these clusters, gravitational interactions play a significant role. As galaxies collide and merge, they can trigger bursts of star formation, which leads to the creation of new stars from the available gas. Moreover, the interactions are not limited to just galaxies. The hot gas present in clusters, which can reach temperatures of millions of degrees, plays a key role in the overall dynamics and evolution. This gas can emit X-rays, offering astronomers vital information about the cluster's mass and composition. Galaxy clusters are not only of interest for their structure and formation process, but also serve as critical tools for understanding the nature of dark matter and dark energy. By studying the dynamics of clusters, researchers can infer the distribution of dark matter while also gaining insights into the rate of cosmic expansion. In this way, galaxy clusters provide a window into both the history and future of the universe, illuminating the intricate web of cosmic evolution. The existence of dark matter and dark energy has been inferred from a variety of observational evidence that cannot be explained by ordinary matter alone. Dark matter, which does not emit, absorb, or reflect light, is believed to make up about 25% of the universe. One of the primary pieces of evidence for dark matter comes from the rotational speeds of galaxies. Observations reveal that galaxies rotate at speeds that should cause them to fly apart if they only contained the visible matter we can observe. However, the presence of unseen mass, or dark matter, provides the necessary gravitational pull to keep these galaxies intact. Another significant line of evidence comes from the behavior of galaxy clusters. When astronomers study these clusters, they often measure their total mass through various methods, such as analyzing the motions of member galaxies and observing the hot gas within the cluster that emits X-rays. The mass calculated from these methods consistently indicates far more mass than what is visible, again suggesting the presence of dark matter. Furthermore, gravitational lensing, where light from distant objects is bent by the mass of a galaxy cluster, provides a means to map the distribution of dark matter. The degree of lensing observed often points to large amounts of unseen mass surrounding the galaxies. On the other hand, dark energy, which is thought to make up about 70% of the universe, is inferred mainly from the observation of the universe's accelerated expansion. In 1998, astronomers discovered that supernovae, which serve as standard candles for measuring astronomical distances, were farther away and dimmer than expected. This unexpected dimming indicated that the universe is expanding at an accelerating rate due to a repulsive force powered by dark energy. Further evidence for dark energy comes from the cosmic microwave background, which reveals that the geometry of the universe is flat. This flatness is consistent with a universe that is dominated by dark energy. Additionally, observations of large-scale structures and the distribution of galaxies across the universe support the idea that dark energy plays a critical role in cosmic evolution. Together, these insights represent compelling evidence for both dark matter and dark energy, even though their precise nature continues to challenge our understanding of fundamental physics. Measuring distances in the universe is a complex task due to the vast scales involved, but astronomers use several techniques, often referred to as distance ladders, which build upon one another to cover different ranges. The most fundamental method for measuring astronomical distances is through parallax. This technique involves observing nearby stars from two different positions in Earth's orbit around the Sun. By measuring the angle of apparent shift against distant background stars, astronomers can calculate a star's distance using simple trigonometry, though this method is only effective for relatively nearby stars, typically within a few hundred light-years. Beyond stellar parallax, astronomers rely on standard candles, which are objects with known luminosities, allowing them to measure distances based on their apparent brightness. A prime example of a standard candle is the Type Ia supernova, a specific kind of exploding star with a consistent peak luminosity. When a Type Ia supernova occurs in a distant galaxy, astronomers can compare its observed brightness to its intrinsic brightness to determine how far away it is. This method is crucial for measuring distances to galaxies that are millions of light-years away. Cosmic distance scales also utilize the tying distance method, which involves measuring the distances to nearby galaxies and then using their properties to calculate distances to more remote groups. For instance, the relationship between a galaxy's mass and its luminosity or the motion of its constituent galaxies can provide additional distance measurements. This method expands astronomers' reach farther into the cosmos while maintaining a level of accuracy. As distances increase in conjunction with these methods, the redshift of galaxies is essential for measuring vast expanses of the universe. The greater a galaxy's redshift, the shift of light toward longer wavelengths, the faster it is receding from us, an effect linked to the expanding universe. By using the redshift measurements alongside Hubble's law, which relates redshift to distance, astronomers can estimate how far away these distant galaxies are, further enhancing our understanding of the universe's structure and composition. Each technique interconnects, creating a robust framework for measuring distances across the cosmos. The nature of dark matter remains one of the most profound mysteries in modern astrophysics, as it constitutes about 25% of the universe's total mass-energy content, yet eludes direct detection. Unlike ordinary matter, which interacts with electromagnetic forces and is therefore visible, dark matter does not emit, absorb, or reflect light. This means that it cannot be detected through traditional astronomical methods that rely on observing light. Instead, scientists infer its existence from gravitational effects on visible matter, like galaxies and galaxy clusters, as well as from its contribution to the cosmic structure. Several leading theories attempt to explain what dark matter could be. The most prevalent hypothesis suggests that dark matter consists of weakly interacting massive particles, commonly known as WIMPs. These particles are predicted to have mass and experience gravitational interactions, but they would only weakly interact with ordinary matter through other fundamental forces. While WIMPs are a prime candidate, extensive efforts to detect them directly in laboratories on Earth have so far failed to yield conclusive evidence. Another potential component of dark matter might be axions, hypothetical elementary particles that are extremely light and would also interact weakly with other matter. Similar to WIMPs, axions would need to be detected through indirect means. They could potentially be produced in high-energy processes and researchers are exploring various experimental methods to observe their effects. Some models also suggest that dark matter could involve modifications to our understanding of gravity itself. Theories such as modified Newtonian dynamics propose that the effects attributed to dark matter could instead arise from changes to gravitational laws at vast distances. While this idea challenges conventional theories of gravity, it highlights the need for a comprehensive understanding of both dark matter and the forces governing the universe. Overall, the true nature of dark matter remains elusive. Ongoing experiments both in particle physics and astrophysics are critical to unlocking its secrets. Each new finding contributes to a more complete picture of the universe, and as researchers delve deeper into this cosmic enigma, they may uncover profound insights into the fundamental workings of reality itself. The accelerated expansion of the universe is primarily attributed to a mysterious force known as dark energy. Discovered in 1998 through observations of distant supernovae, this phenomenon revealed that the rate at which the universe expands is not only continuing, but actually increasing over time. Dark energy is thought to constitute roughly 70% of the universe's total energy content, and its exact nature is one of the greatest puzzles in cosmology. Researchers have theorized that dark energy could take various forms. One leading explanation is that it may be a constant energy density that fills space homogeneously, known as the cosmological constant. This idea was first proposed by Albert Einstein in the early 20th century when he introduced it into his equations of general relativity to allow for a static universe. After discovering that the universe is expanding, he famously referred to this term as his greatest blunder. However, the concept regained significance in light of the accelerating expansion observed in the late 20th century. Another possibility is that dark energy could be dynamic, meaning that its properties could change over time or vary across space. These forms include quintessence, a field similar to a scalar field that could evolve. Such theories suggest that dark energy may behave differently in the early universe than it does now, potentially impacting cosmic evolution in significant ways. The effects of dark energy are profound, influencing the ultimate fate of the universe. If the acceleration continues indefinitely, it could lead to a future scenario known as the Big Freeze, where galaxies drift apart over unimaginable distances, eventually resulting in an isolated and cold universe. This outcome would signify a cosmic fate heavily dominated by dark energy, altering the structure of the universe as we know it. As scientists work to unlock the mysteries of dark energy, they employ various observational techniques, including studying the cosmic microwave background and the large-scale structure of the universe. These efforts aim to gather more data and refine our understanding of the underlying mechanisms driving the accelerated expansion. Each discovery brings us closer to resolving this cosmic enigma and reveals more about the fundamental nature of our universe. The concept of other universes existing beyond our own falls within the realm of theories concerning the multiverse, a term that describes a hypothetical collection of multiple universes that together comprise everything that exists. While the notion of a multiverse is intriguing and appears in various scientific frameworks, it remains largely speculative and lacks direct empirical evidence. One of the most prominent theories suggesting the existence of a multiverse comes from cosmic inflation, the rapid expansion of the universe that occurred just after the Big Bang. According to some models of inflation, as different regions of space underwent this exponential growth, they may have stopped inflating at different times. This could lead to pocket or bubble universes that each have distinct physical properties and constants, effectively creating a vast landscape of universes with varied characteristics. In this model, our observable universe is merely one bubble in a much larger multiverse. Another framework that predicts the existence of multiple universes arises from string theory, which attempts to unify all fundamental forces in nature and describe the underlying principles of particles and gravity. String theory suggests that multiple dimensions exist beyond the three spatial dimensions, and one temporal dimension we experience. Different configurations or compactifications of these extra dimensions could result in a multitude of universes, each with its own laws of physics. However, the existence of other universes remains a topic of debate among scientists. While mathematical models can suggest plausibility, direct observational evidence is challenging to obtain. Most current observations focus exclusively on our own universe, and exploring realms beyond remains difficult with our existing technology. The question of whether other universes exist provokes deep philosophical inquiries about the nature of reality and our understanding of existence. Ultimately, while the notion of a multiverse captivates both scientists and the public alike, it remains a fascinating area of theoretical research. As our understanding of physics and cosmology evolves, we may develop new insights that either confirm or rule out the existence of other universes, enriching our comprehension of the cosmos as a whole. The question of what happened before the Big Bang invites profound philosophical and scientific inquiries, as our current understanding of the universe begins with the Big Bang itself, which marks the beginning of both time and space as we know them. According to the prevailing cosmological model, the universe was once concentrated in an extremely hot, dense state, which then rapidly expanded, leading to the creation of space and time. This creates a dilemma when considering conditions before the Big Bang, as time is inherently tied to the fabric of the universe that began with that event. Some scientists propose that the concept of before the Big Bang might be meaningless within the traditional framework of physics. The equations of general relativity, which describe the gravitational force and the curvature of spacetime, break down under such extreme conditions, suggesting that our current models are insufficient to provide answers about the state prior to the Big Bang. The singularity, a point at which density and curvature of spacetime become infinite, implies that conventional notions of time do not apply. Various theories attempt to address this question, one of which is the idea of a cyclical universe. This model posits that the universe undergoes endless cycles of expansion and contraction, where each Big Bang is followed by a big crunch, leading to a subsequent re-expansion. Some proponents of this theory suggest that events prior to our current universe's creation may exist in a continuous loop of universes. Another intriguing possibility comes from the framework of quantum gravity, which attempts to reconcile general relativity with quantum mechanics. Some models suggest the existence of a pre-Big Bang state, where quantum fluctuations could give rise to the Big Bang itself. In this scenario, the universe could potentially evolve from a different set of conditions or realms, bypassing the limitations of conventional time. While these theories provide intriguing perspectives, none can be definitively proven due to the lack of observational evidence from before the Big Bang. The quest to understand the origins of the universe, including what may have preceded the known cosmos, remains an area of active research and speculation. As scientists continue to explore the fundamental principles of physics, new insights may eventually emerge to illuminate this enigmatic chapter of existence. The asymmetry between matter and antimatter in the universe, where there is a predominance of matter, is one of the most perplexing questions in modern cosmology and particle physics. According to current theories of particle physics, when the universe emerged from the Big Bang, it produced equal amounts of matter and antimatter. Antimatter consists of particles that have properties opposite to those of ordinary matter, such as the electron's counterpart, the positron. If equal amounts of matter and antimatter had survived, they would have annihilated each other upon contact, resulting in a universe dominated by radiation rather than the matter we observe today. Several hypotheses attempt to explain why our universe is so skewed toward matter. One leading idea is called baryogenesis, which postulates that certain processes in the early universe favored the production of baryons, the particles that constitute normal matter, over antibaryons. These processes might involve interactions during conditions that prevailed in the early universe, potentially influenced by phenomena such as CP violation, where the laws of physics treat particles and antiparticles differently under certain conditions. This violation could create a slight excess of matter during the high-energy interactions that took place shortly after the Big Bang. Another perspective involves the idea of lepton asymmetry, suggesting that certain interactions involving leptons, another category of elementary particles, could also lead to an imbalance favoring matter over antimatter. In this scenario, neutrinos and their counterparts might play a critical role in producing the observed excess of baryons over antibaryons. Researchers have been investigating these processes through various experiments, both in large particle colliders and in astrophysical observations. Despite these theories, the precise mechanism that resulted in this matter-antimatter discrepancy remains unresolved. Exploring this question is crucial, not only for understanding the evolution of the universe, but also for gaining insights into the fundamental laws of physics. Each new piece of data collected from experiments and observations may help unveil the missing links that explain how we ended up in a matter-dominated universe, igniting a deeper understanding of the cosmos and its origins. The ultimate fate of black holes is a captivating and complex topic that intertwines aspects of general relativity, quantum mechanics, and cosmology. Initially formed from the remnants of massive stars after they exhaust their nuclear fuel, black holes possess gravitational fields so intense that not even light can escape them. Their ultimate fate, however, is not as straightforward as one might expect. One predominant theory regarding the fate of black holes is Hawking radiation, proposed by physicist Stephen Hawking in the mid-70s. According to this theory, black holes are not completely black. They emit tiny amounts of thermal radiation due to quantum mechanical effects near their event horizons. Over incredibly long timescales, this emission leads to a gradual loss of mass. If this process continues, black holes could eventually evaporate completely. For stellar mass black holes, this timescale is immense, often exceeding the current age of the universe. When considering supermassive black holes, which can contain millions or billions of times the mass of our Sun, their fate remains similarly intriguing. While they also would lose mass through Hawking radiation, the rate of this evaporation is remarkably slow compared to their massive scale. As the universe continues to expand, the environment around these black holes may change dramatically, affecting their interactions with surrounding matter and the eventual rate of their evaporation. Another scenario involves the merger of black holes. As they interact gravitationally with nearby objects, they can gain mass by consuming matter or merging with other black holes. This process may create increasingly larger black holes until they eventually succumb to the process of Hawking radiation. Yet even in this scenario, the timescale for such events surpasses current human timescales by vast amounts. The ultimate fate of black holes, therefore, sets the stage for intriguing questions concerning the future of the universe itself. As the cosmos continues to evolve, black holes may play a significant role in shaping the fate of galaxies and the universe at large. While the complete understanding of their destiny remains an active area of research, each new discovery brings us closer to unraveling the mysteries at the heart of these enigmatic entities. The end of the universe is a topic that fascinates cosmologists and philosophers alike, and several theories propose different scenarios for how it may ultimately unfold. Among the most discussed possibilities are the Big Freeze, the Big Crunch, and the Big Rip, each resulting from various factors such as the effects of dark energy, the density of matter, and the overall geometry of the universe. The Big Freeze, also known as heat death, is the most widely accepted scenario given current observations of accelerated expansion. In this model, the universe continues to expand indefinitely as dark energy drives the acceleration. Over vast eons, galaxies will drift farther apart and the stars will burn out, leading to a cold, dark cosmos. Eventually, all stars will extinguish, black holes will evaporate through Hawking radiation, and the universe will reach a state where temperatures approach absolute zero, with only scattered particles remaining in a vast empty space. Conversely, the Big Crunch hypothesizes that the universe's expansion could reverse if its density exceeds a critical threshold. In this scenario, gravity would eventually pull all matter back together, culminating in a singularity, similar to the conditions at the beginning of the universe. As galaxies, stars, and planets collapse inward, temperatures and densities would rise dramatically until the universe collapses into a hot, dense state, potentially leading to another Big Bang, a cycle repeating in an infinite loop of expansion and contraction. The Big Rip presents an alternative fate where the universe's expansion does not merely continue, but accelerates uncontrollably due to an unusual form of dark energy that grows stronger over time. In this scenario, galaxies would eventually be torn apart, followed by solar systems and ultimately even atoms, leading to a complete disintegration of all matter in the universe. The timeline for this scenario is also vast, but suggests a dramatic and violent end. While these three scenarios are among the most prominent, other theories exist, such as the idea of a multiverse that posits the universe may simply give rise to new ones in a more complex ecosystem of realities. Each of these potential outcomes informs our understanding of the fundamental nature of reality and cosmic evolution. Although we are far from knowing the definitive fate of the universe, ongoing research in cosmology continues to expand our grasp of the cosmos and the intricate possibilities of its future. The formation of stars in the universe is a process intricately tied to the availability of gas and dust, primarily in the form of hydrogen and helium, which are the building blocks of stellar formation. Currently, stars are still forming, particularly in regions known as stellar nurseries or molecular clouds, where these materials are abundant. However, the rate of star formation is gradually declining over cosmic time. As the universe evolves, it expands, and the density of matter decreases. This decline in density means that there will be less gas available to collapse under gravity to form new stars. Moreover, over billions of years, stars will exhaust the available material in the form of heavy elements created during their lifetimes. When massive stars explode as supernovae, they disperse enriched materials back into space, but eventually the overall amount of gas available for star formation will diminish. Current models suggest that star formation will continue for several tens of billions of years. Early in the universe's history, star formation rates were much higher, with a significant number of massive stars forming within just a few billion years after the Big Bang. However, as time progresses, the formation of new stars will slow down and eventually reach a point when it becomes exceedingly rare. Ultimately, it is predicted that star formation will diminish significantly, perhaps ceasing altogether in around 100 trillion years, when the universe moves toward a state of stellar dormancy. Most stars will be older, and more will have died, with only a dwindling number of smaller stars and brown dwarfs remaining. The future universe will then become a dimmer and quieter place, with far fewer stellar births. In this distant future, any ongoing formation would likely consist of less massive stars, and even then, the conditions for star formation would be drastically different from those we observe today. Understanding the timescale and processes of star formation provides crucial insight into the evolution of galaxies and the cosmic ecosystem that birthed the stars we see in the night sky. The impending collision between the Milky Way and the Andromeda Galaxy, which is expected to occur in approximately 4 billion years, is a monumental event in cosmic terms. This collision is part of the natural evolution of galaxies, driven by gravitational attraction as they approach each other within the vast expanse of space. Currently, Andromeda is on a collision course with the Milky Way, moving toward us at a speed of about 110 kilometers per second. As the two galaxies begin to interact gravitationally, they will not collide in a catastrophic sense, as most of the space within galaxies is primarily empty. Instead, the gravitational attraction will distort their shapes, leading to spectacular encounters. Gas and dust will compress, triggering bursts of star formation as dense regions collapse into new stars due to the gravitational instabilities created by the two galaxies intertwining. This period will be marked by vibrant new stellar populations being born amid the turmoil. The collision will unfold over several billion years, eventually leading to the merger of the two galaxies. As the Milky Way and Andromeda continue to interact, they will form a new galaxy often referred to as Milkomeda or Milkdromeda. This process will involve intricate dance-like movements as the remnants of both galaxies overlap, leading to complex structures and possibly a more elliptical shape once the merger concludes. In the process, some stars will be flung out into intergalactic space, while others may find themselves temporarily orbiting around the central regions of the combined galaxy. One of the remarkable features of this event is that despite the massive scale of both galaxies, individual stars are unlikely to collide due to the vast distances between them. However, the interactions will profoundly affect the dynamics and structure of the resulting galaxy. The collision of the Milky Way and Andromeda offers a unique opportunity to study galaxy evolution and the life cycle of galaxies. As astronomers gather more data about the movement and composition of both galaxies in preparation for this eventual merger, they gain valuable insights into the metabolic processes of the cosmos and the historical narratives of our place in the universe. Ultimately, while this crash may sound catastrophic, it marks a transformative chapter in the universal dance of galaxies. Dark energy plays a pivotal role in shaping the long-term evolution of the universe, fundamentally influencing its fate and expansion rate. This mysterious force, which constitutes about 70% of the universe's total energy content, drives the accelerated expansion we observe today. Understanding how dark energy affects the cosmos involves examining its properties and implications for the universe's future. The most widely accepted explanation for dark energy is the cosmological constant, a term added to Einstein's equations of general relativity. According to this model, dark energy has a constant energy density that fills space uniformly and exerts a repulsive force, counteracting the attractive force of gravity. This leads to a scenario where galaxies continue to move away from each other, increasingly accelerating as dark energy dominates the dynamics of the cosmos. As the universe expands further, the effects of dark energy will become even more pronounced, potentially leading to a situation where star formation slows, existing stars fade, and the universe becomes progressively darker. In the long term, if the accelerated expansion continues, it could lead to a fate known as the Big Freeze or heat death, where the universe cools to near absolute zero as stars extinguish and galactic structures disperse. Over trillions of years, galaxies will drift apart, and any ongoing star formation will dwindle drastically, producing a universe that is increasingly empty and devoid of light. The result will be a vast, lonely expanse filled with cold remnants of stars and dark matter. Another intriguing aspect is that dark energy may have dynamic properties that evolve over time or vary across space. If dark energy were to change in strength or nature, it could result in different scenarios for the universe's evolution. For instance, if dark energy were to decrease, the expansion could slow, possibly leading the universe toward a cycle of gravitational collapse known as the Big Crunch. Conversely, an increase in dark energy could result in an even faster expansion, leading to scenarios such as the Big Rip, where galaxies, solar systems, and even atoms are eventually torn apart. Overall, dark energy is a central force in determining the ultimate fate of the universe, making it a crucial focus of current research in cosmology. As scientists aim to understand its nature and impact, they continue to deepen our comprehension of the universe's evolution and the fundamental forces that govern reality. Each breakthrough in this area could reshape our understanding of the cosmos and its grand trajectory over immense timescales. The heat death of the universe is a theoretical end state of the cosmos that arises from the second law of thermodynamics, which states that in a closed system, entropy tends to increase over time. Entropy can be interpreted as a measure of disorder or the number of ways that a system can be arranged. As the universe expands and ages, it will evolve toward a state of maximum entropy and thermal equilibrium, leading to a scenario where no useful energy remains to perform work. In this heat death scenario, the universe will continue to expand indefinitely. Stars will eventually exhaust their nuclear fuel and cease to shine, leading to a dark and cold environment. As stellar systems decay, the remnants of stars, including white dwarfs, neutron stars, and ultimately black holes, will dominate the cosmos. Any remaining stellar objects will cool down over an immense timescale, and all forms of energetic processes will largely come to a halt. Extended over trillions of years, black holes themselves may also evaporate through Hawking radiation, a process that would very gradually siphon off their mass, ultimately leading to their disappearance. The heat death assumes that as time progresses, all energy will be evenly dispersed throughout the universe. This state of maximum entropy implies that there are no temperature gradients or differences in energy, rendering the universe lifeless and static, essentially a vast and uniformly cold expanse of sparse matter. As energy availability drops to near absolute zero, the universe will reach a point where no further processes can occur, leading to an absence of structure or complexity. This results in a scenario where any form of life, star formation, or dynamic activity ceases to exist. If the universe does indeed progress towards this heat death, it represents the final, quiet stage of cosmic evolution, where change becomes imperceptible and the universe remains in a state of lingering stillness. The heat death is just one possible fate of the universe, and while it is grounded in the principles of thermodynamics, ongoing research and discoveries about dark energy and cosmic structure continue to shape our understanding of the universe's long-term evolution. Each new finding contributes to our larger narrative about existence and the transformative journey of the cosmos over unimaginable timescales. The idea that a new universe could emerge from the end of our current one is a fascinating concept that resonates with various cosmological theories, while the precise mechanisms behind such a scenario remain speculative. Certain models in theoretical physics suggest pathways for the rebirth or creation of new universes. One prominent idea is rooted in the theories of cosmic rebirth through a cyclic universe model. This theory posits that the universe undergoes infinite cycles of expansion and contraction. In this view, after reaching a stage like the Big Crunch, where the universe collapses back into a singular state, it could then trigger a new Big Bang, leading to the birth of a fresh universe. Each cycle would be distinct, potentially having different physical constants or laws governing its evolution. This cyclical nature would mean that the end of one universe could seamlessly give way to the beginning of another. Another intriguing possibility arises from the concept of quantum fluctuations in a vacuum. Some physicists speculate that new universes could spontaneously form through fluctuations in a quantum vacuum, wherein energy fluctuations lead to the creation of bubbles that rapidly expand into new universes. In this scenario, such bubbles could possess distinct properties and may not necessarily resemble our current universe. The idea of a multiverse emerges from such models, suggesting countless universes, each with varying characteristics and dimensions. Additionally, theories related to string theory propose that the fabric of the cosmos is more complex than our current understanding. In some cases, regions of space could give rise to new physical realities, leading to multiple coexisting universes. These ideas often challenge the conventional views of time and space, introducing abstract notions that extend our comprehension of existence beyond the confines of our universe. However, it's important to note that these concepts remain largely speculative and are not yet substantiated by empirical evidence. While they provide tantalizing visions of cosmic possibilities, significant gaps in our understanding of fundamental physics remain. The nature of time, gravity, and quantum mechanics still need resolving to clarify whether a new universe could indeed emerge from a previous one. As research in cosmology and theoretical physics advances, we may eventually unlock the secrets of the universe and explore the potential connections between cosmic beginnings and endings. Each incremental revelation brings us closer to understanding the intricate tapestry of existence and the complex interplay between universes. Our understanding of cosmic history profoundly shapes our perspective on humanity's place in the universe. As we delve into the origins and evolution of the cosmos, from the Big Bang to the formation of galaxies, stars, and planets, it becomes clear that we are a relatively recent development within a vast and ancient universe. This context leads to both humbling realizations and existential questions about our existence and significance. The timeline of cosmic history reveals that the universe is approximately 13.8 billion years old, with the first stars forming just a few 100 million years after the Big Bang. In contrast, human civilization has existed for only a few thousand years, making our presence but a fleeting moment in the grand scale of cosmic time. This vast age can evoke a sense of insignificance, illustrating how ephemeral human achievements and concerns are in relation to the unfathomable timescales of the universe. However, this cosmic chronology also highlights the remarkable circumstances that allowed life and consciousness to emerge. The conditions necessary for the formation of stars and planets, and ultimately for life, are incredibly complex and rare, suggesting that while we may be just a blip in cosmic history, our presence is the product of numerous finely tuned processes. This rare convergence of conditions can inspire a sense of wonder and a recognition of our unique position as conscious beings capable of exploring and understanding the cosmos. Moreover, understanding cosmic history fosters an appreciation for the interconnectedness of all matter in the universe. Elements essential for life, such as carbon and oxygen, are forged in the hearts of stars and dispersed throughout space during supernova explosions. This realization emphasizes that we are not separate from the universe. Rather, we are made of star stuff, intimately linked to the processes that govern the cosmos. Our cosmic history instills a profound responsibility to seek knowledge, protect our planet, and consider the broader implications of our existence. As we explore the universe and contemplate the potential for life beyond Earth, the awareness of our fragile yet remarkable position becomes even more vital. Each discovery in cosmic history enriches our understanding of who we are, where we come from, and how we relate to the vast, timeless expanse of the universe. Ultimately, this journey encourages us to participate actively in the ongoing story of existence, recognizing our role within the intricate tapestry of the cosmos. The long-term survival of humanity in an evolving universe presents a multitude of challenges and possibilities, influenced by both cosmic conditions and our capacity for adaptation. As the universe continues to change over billions of years, humanity will need to confront issues related to resource availability, environmental conditions, and the potential for technological advancement. These factors will play crucial roles in determining our future. One compelling possibility involves space colonization. As the conditions on Earth evolve, whether due to climate change, natural disasters, or cosmic events, human populations might seek refuge in off-world habitats. Mars, with its relatively accessible resources and potential for terraforming, is often considered a viable candidate. Other celestial bodies, such as moons and asteroids, could serve as stepping stones for broader exploration and settlement. Developing technology for sustainable living in these environments will be critical as humanity expands beyond Earth. The advent of advanced technologies may also offer pathways for adapting to changing conditions in the universe. This could include the development of life-sustaining systems that harness resources from inhospitable environments, or the creation of artificial intelligence capable of managing complex ecological systems. Biotechnology and genetic engineering could provide humans with enhanced adaptability, allowing us to survive in diverse environments, whether on distant planets or in space habitats. Moreover, the long-term survival of humanity may depend on the ability to foresee and respond to cosmic threats, such as asteroid impacts or solar flares. Developing adequate defense mechanisms and early warning systems will be crucial for mitigating risks that could jeopardize human existence. The pursuit of knowledge about these threats and their potential impacts could empower humanity to take precautionary measures, enhancing our resilience. Ultimately, as the universe continues to evolve and present challenges, humanity will need to cultivate a spirit of cooperation, scientific inquiry, and adaptability. The journey through space exploration, technological advancement, and ecological stewardship will be paramount for ensuring a future where humanity can thrive. While uncertainties will inevitably accompany this venture, fostering a proactive approach to cosmic change may unlock pathways for long-term survival and growth in an ever-evolving universe. Each step we take in understanding and embracing the cosmos will shape our role in the grand narrative of existence. Future technologies hold immense potential for enhancing our exploration and understanding of cosmic processes, potentially allowing humanity to manipulate the very fabric of the universe. As our scientific knowledge advances and our technological capabilities expand, several areas are particularly promising for altering how we interact with cosmic phenomena. One of the most exciting prospects lies in astrophysics and space travel technologies. Enhanced propulsion systems, such as nuclear thermal propulsion or concepts like ion drives and antimatter engines, could enable us to reach distant celestial bodies more efficiently. This would facilitate not only the exploration of planets and moons within our solar system, but also send missions toward nearby star systems. Advanced telescopes and observational tools may allow us to gather more detailed information about exoplanets, their atmospheres, and potential biosignatures, ultimately helping us assess their habitability. Another area of potential is the development of technologies for manipulating energy on a cosmic scale. Concepts linked to harnessing stellar energy, such as Dyson spheres or swarms, are theoretically capable of capturing a star's energy output for use in civilization. Engineering projects of this magnitude would offer vast energy resources, enabling extensive cosmic endeavors, including terraforming other planets or sustaining large-scale settlements in space. In the realm of cosmology, insights derived from quantum mechanics and general relativity might lead to breakthroughs that allow for the manipulation of gravitational forces. Projects like gravitational wave detection and deeper understandings of dark matter and dark energy could one day unlock new means to influence gravitational fields. This would deepen our understanding of cosmic dynamics and possibly create technologies capable of propulsion or stabilization in regions of strong gravitational influence. The manipulation of cosmic materials may also find practical applications through advanced materials, science, and nanotechnology. Fabricating structures and habitats in space could become feasible with the ability to efficiently use in-situ resources, such as mining asteroids for metals or utilizing lunar regolith for building materials. In this way, humanity could create self-sustaining colonies or outposts scattered throughout the solar system, enhancing our presence in the cosmos. Ultimately, the integration of artificial intelligence and machine learning into these technologies will help accelerate our understanding of cosmic processes and refine our approaches to exploring the universe. With ongoing advancements in these fields, the possibility of not only exploring but also actively modifying our interactions with cosmic phenomena becomes increasingly tangible. While many of these ideas remain in the theoretical phase, each step forward in technology could lead to transformative changes in how we perceive our place in the universe and the potential we hold for shaping our cosmic future. As humanity stands on the brink of advanced technologies that could alter the course of cosmic evolution, a myriad of ethical considerations emerges. These concerns encompass not only our impact on Earth and its ecosystems, but also the broader implications of manipulating celestial phenomena. Navigating these ethical dilemmas will require thoughtful discourse and a framework that prioritizes responsibility and foresight. One pressing ethical concern revolves around the environmental impact of our actions, particularly as we consider space colonization or the exploitation of extraterrestrial resources. Intervening in cosmic processes or colonizing other planets raises questions about the preservation of their ecosystems if they exist. Should humanity strive to terraform an inhospitable planet, we must consider the potential consequences for any existing microbial life or ecosystems, as well as the ethical implications of altering entire planets for human habitation. Striking a balance between human needs and the integrity of other worlds poses a complex challenge. Furthermore, the risks associated with manipulating cosmic phenomena cannot be overlooked. Efforts to harness and control energy from stars or attempts to redirect asteroids for resources could have unintended consequences. The potential to trigger catastrophic events, such as changing the orbits of celestial bodies or creating unstable cosmic pathways, necessitates a serious ethical examination of our motivations and the procedures involved. Decisions made in the name of progress must be carefully weighed against the risks posed to both our own planet and the wider cosmos. The potential for inequalities in access to advanced technologies also raises significant ethical implications. As these technologies develop, disparities in who can wield such power, whether nations, corporations, or individual entities, could lead to exploitation or conflict. Questions concerning stewardship arise. Who gets to decide how cosmic resources are utilized, and who benefits from advancements made in manipulating cosmic processes? Ensuring equitable access and shared benefits while maintaining global cooperation will be crucial in navigating these challenges. The ethical considerations extend to the philosophical realm as well. As we gain the technological capability to alter cosmic processes, we must confront questions about our role in the universe. Does humanity have the right to take such responsibility? What does it mean to be a steward of the cosmos? And how do we reconcile this with our historical tendencies toward environmental degradation on Earth? These philosophical reflections will shape our identity as a species and influence how we engage with the universe. As our capabilities evolve, a proactive and inclusive approach to ethics will guide humanity in making responsible choices about altering cosmic evolution. Engaging diverse perspectives, from scientists and ethicists to the public, will foster a comprehensive understanding of the implications of our actions and ensure that our exploration of the cosmos is grounded in a framework of respect, responsibility, and humility. Balancing ambition with caution will be essential in shaping our cosmic legacy. The vast scale of cosmic time and space profoundly influences human philosophy and culture, shaping our perceptions of existence, purpose, and our place within the universe. The enormity of the cosmos challenges our everyday intuitions about time and significance, prompting deep reflection on the nature of reality and the meaning of human life. Philosophically, the immense timescales of the universe often lead to existential questions about the significance of human existence. The realization that the universe is approximately 13.8 billion years old positions our brief lives, often spanning a mere few decades, within a strikingly short context. This perspective can provoke feelings of insignificance, compelling individuals to ponder what it means to be alive in such a vast cosmos. Many philosophical traditions grapple with these feelings, leading to varying interpretations of meaning, spirituality, and responsibility. For some, the enormity of the universe emphasizes the fragility and preciousness of life, encouraging a deeper appreciation for our experiences and connections. Culturally, the portrayal of the universe and our place within it has inspired countless works of art, literature, and music. Artists and writers have often drawn upon the themes of cosmic wonder, exploration, and the unknown to convey complex emotions and ideas. The imagery of stars, galaxies, and the cosmos serves as a backdrop for exploring human aspirations, fears, and relationships. This artistic engagement reflects a deep-seated curiosity about the mysteries of the universe, encouraging societies to foster a sense of connection not only to each other, but also to the greater cosmos. Additionally, the scientific pursuit of understanding the universe has shaped cultural narratives and worldviews. The advancement of cosmology, physics, and astronomy has sparked shifts in understanding that can fundamentally alter cultural beliefs about our origins. From Copernicus to Darwin and Einstein, these groundbreaking ideas have gradually reshaped humanity's self-perception, emphasizing the interconnectedness of all things and spotlighting the intricate relationships found within the cosmos. This shift resonates in contemporary discussions about climate change, technological development, and our responsibilities toward the planet and each other as we grapple with our cosmic heritage. Furthermore, the vastness of space can also foster a sense of unity among people, transcending cultural, geographic, and political divisions. The shared endeavor to explore the cosmos, represented through international collaborations in space missions and scientific research, evokes a spirit of cooperation and collective aspiration. Celebrating human achievements in understanding the universe taps into a sense of shared identity that can bridge cultural boundaries and foster a common vision for the future. Ultimately, the vast scale of cosmic time and space serves as a powerful catalyst for human thought, inviting contemplation about existence, purpose, and our interconnection with the universe. By examining these themes, societies may cultivate a rich tapestry of beliefs, values, and aspirations that not only deepen our comprehension of ourselves, but also illuminate our journey through the cosmos, fostering a continuous dialogue between science, philosophy, and culture. In the context of cosmic history, humanity bears a profound responsibility to preserve and protect life, shaped by our understanding of the fragile and intricate nature of existence. As we consider the vast narrative of cosmic evolution, from the formation of stars and galaxies to the emergence of life itself, it becomes evident that our actions have consequences that extend beyond immediate concerns, influencing the long-term trajectory of life on Earth and potentially throughout the cosmos. One primary aspect of this responsibility lies in recognizing our interconnectedness with the broader web of life. The elements essential for life were forged in the hearts of stars, and our very existence is a product of processes that have unfolded over billions of years. Understanding this connection calls for a deeper respect for the natural world, urging us to protect biodiversity and ecological systems. The loss of species and habitats disrupts the delicate balance of life, and as stewards of the Earth, it is imperative to adopt sustainable practices that preserve the environment for future generations. Moreover, the lessons drawn from cosmic history highlight the importance of foresight. Throughout the universe's evolution, conditions have shifted dramatically, leading to mass extinctions and changes that render environments inhospitable. Currently, humanity faces unprecedented challenges, including climate change, habitat destruction, and pollution, driven largely by our activities. Recognizing the potential long-term impacts of these actions compels us to adopt responsible stewardship, ensuring that we do not inadvertently create conditions that threaten the survival of life as we know it. Additionally, as we venture into space exploration and potential colonization of other planetary bodies, the ethical considerations of our actions will grow increasingly important. Should we discover microbial life on other planets, our responsibility to protect these extraterrestrial ecosystems will become a critical topic of discussion. The potential for altering other worlds, whether through terraforming or resource extraction, brings forth questions about our role as caretakers. Ensuring that our actions are guided by respect for the unknown and the preservation of life will be crucial in establishing our interstellar legacy. Finally, this cosmic awareness encourages a collective ethos of compassion and cooperation. The realization that humanity is a small entity within the vast, indifferent universe fosters a sense of unity and purpose. By collaborating across borders to mitigate existential threats and promote conservation efforts, we can amplify our impact and create a culture that prioritizes the preservation of life. This shared responsibility extends beyond our planet, inviting us to consider our role within the broader cosmic community. The responsibility to preserve and protect life, informed by our understanding of cosmic history, calls for a profound commitment to safeguarding our planet and recognizing our interconnectedness with all living beings. By approaching our stewardship with wisdom, foresight, and ethical considerations, we engage in a sacred duty that transcends time and space, ensuring the continuity of life in our dynamic universe.